All right, let's get this party going. So hello, everyone. Welcome to XDC 2024. For those of you that I haven't had a chance to meet yet, my name is Mark Filio. I'm a senior marketing manager at Collabra, and I'm also a very proud member of the X.Org board since 2020. So I'm on my third mandate right now. So thank you to everyone who voted for me. I don't know who, but thank you. All right, let's get things going. So first off, welcome back to Montreal. I know a bunch of you were here back in 2019, so I'm super happy to see everyone back here 5 years later. A lot of things changed, but a lot of faces I've seen before, so it's nice to see that the community is still sticking together. First things first, because a lot of people asked me about it, the Wi-Fi information. It was listed out front, but I figured I'll put it up front here too. So basically, you just have to select Concordia Guest, put in the access code. There's a little pop-up that asks you for information. I just put my first name and it was all good. And it should be good for the rest of the week. I noticed on my phone it asked me to log in again today, but on my laptop it worked all week. But if it doesn't, you just have to refill that thing and it takes a second to connect. Anyway, I'll have the slide back up at the end too, so if you don't have a chance to write it down now, I'll have it back after. First and foremost, XDC wouldn't be possible without our sponsors. So I wanted to give a shout out to our platinum sponsor, Collabra, who gave me the opportunity to organize. Big hand. Our gold sponsors, which we couldn't do without as well, ARM. Andrew is here. Thank you, Andrew. Google, Microsoft, and NVIDIA. Big hand of applause as well. Our silver sponsors, AMD, FEX, EMU, Igalia, Qualcomm, and the Linux Foundation. So thank you guys as well. Very, very important to have you on board. And last but not least, our bronze sponsors, CodeWeavers, Chronos Group, and LibComputer. So thank you as well. Worth mentioning, I'm super proud to say that this year we had a total of 13 sponsors, which was a new record for XDC. So it's really nice to see that the community and these companies are supporting us and are growing numbers every year. So who knows, maybe we can get to 15 next year. That would be great. And I know there's a couple of companies that we've been talking to that said they might join next year, so fingers crossed. Speaking of bronze sponsors, I know you found out when you arrived this morning, but our bronze sponsor, LibComputer, had a gift for our attendees today. So they gave everyone a Solitude AML S905. It's their second generation Cottonwood hardware that features the AI accelerator, an Amlogic S905. But most important by far is that very last bullet. It's upstream nearly everything. There's always a little thing that's not fully upstream, but everything else is upstream. and it runs the Mali, so it's supported by Panfrost. So really cool to have. So big thanks to LibComputer for bringing that surprise today. Really appreciate it. They had done that too back a couple of years ago and decided to do it again this time. So thank you, LibComputer. Big hands of applause as well. Just a reminder, we have an updated website. If you want to stay connected, it'll be updated regularly this week. And we also have the events list where I've been sending a couple updates, so it's the best place to get the XDC updates. And we're trying to be active on Mastodon, not as easy as other channels that we've used in the past, but there's more and more people following us on Mastodon, so follow us on there too to get the latest updates. It's really nice to see that the community is growing on there as well. I was a bit worried when other not mentioned social media networks started being special that we changed, but it ended up turning out really well, and it's growing really well, so kudos to the community there as well. All right, more useful information. As you saw this morning, breakfast is provided every day, and during the coffee breaks too, we'll have snacks as well, so you're good to go there. For lunch, you're free to roam the area. I just put a quick URL there that points to the Google Maps, but there's a ton of restaurants around here because it's basically like a downtown campus, so there's restaurants galore, so you can walk around and find whatever you feel like having for lunch. So you've got time today and tomorrow to walk the streets and find a place to go. Next up, tonight, big difference. In previous editions, our welcome party was the night before it started. This year, we decided let's do it the first night when everyone has arrived, has gotten some rest. So tonight, we'll be having our welcome party at Trois Brasseurs. So it's in Old Montreal. It's like, give you a chance to see Old Montreal for those of you who have never been. It's located on one of the first streets ever built in Old Montreal. So it's a really beautiful street. And anytime you Google Old Montreal, it's literally that street that shows up first in the pictures. So it'll be an opportunity to check it out. When you show up there, it's from 7 to 11. You walk in, go up to the second floor. We have drinks and food provided. And all of it is sponsored by Collabra. So big thanks again to Collabra for sponsoring our welcome event tonight. And I hope that you'll all be joining us. So 7 p.m. sharp, don't miss it. All right, this year's schedule. Big new thing this year is we decided to switch things around. In the past, we've always had 3 days of talks and then people going in and out to meetings, workshops, and whatnot. And we figured, a lot of people came up to us saying it would be nice if people stuck around and just focused on the talks for a couple of days and then focused on meetings and workshops and hacking and whatnot, because we've never had actual Hackfest for XDC. So this year we're trying something new. As you've seen the schedule, we have 2 days back-to-back talks. And then the third day on Friday is entirely for workshop meetings and hacking. I'll get back to that in a second. A reminder for the lightning talks, we have one block tomorrow that starts at 4:45, and then we have a shorter block Friday afternoon. For those of you, we got about a dozen lightning talks. It's 5 minutes, so you gotta stick to that. And I need all of the speakers to upload their slides on Indico, the ones that have lightning talks. So that will allow me to put it all together in one big block. Hopefully it'll work well, but I'll be able to go faster, especially for the recording. If you have only one file, we can go back to back to back to back. So yeah, come see me if you not too sure how to add it to Indico, but it's pretty straightforward. Just log in and you can see a place to upload your files. Also new this year, and I'm especially proud of that. This week has been our very first free desktop week, which basically enabled us to bring together both the GSteamer conference and XDC co-located, same venue, same time. It had never happened before. And I was always a firm believer that free desktop communities should come together and get a chance to collaborate instead of just talking on mailing lists. They should get a chance to meet and see it face to face and talk. So basically this week, Monday and Tuesday, we had the conference in this room. And today and tomorrow, we have XDC right here. And then right across the hall, we have the GStreamer Hackfest. And it's open for everyone, so you can walk back and forth, go meet some of the devs there, come back here, you know. Anyway, nice opportunity for everyone to meet and mingle. I hope it's something that will keep going in the years ahead, but it's also something new that had never happened before. So I'm super happy to see that it worked out this year and that we have both communities together in one place. So it shows the strength of free desktop. So super proud of that. All right. Just to get a summary of the layout, ABCD is where we are. Right across, EFG is where the Hackfest is. So it's right in front. And the lounge area, yeah, that's where you were this morning, where the breakfast and breaks were. As I mentioned earlier, Friday we have workshop meetings and hacking. We already have 2 meetings that are planned. So we have a display KMS meeting and a Wayland workshop. We have the entire floor on Friday. So submit your ideas if you want to get some meetings in. I saw a couple ideas that were submitted already that we'll approve today. But if you got some more meetings or something you want to suggest, submit it on the website and we'll schedule it. We got tons of space, so we can totally make it work. And just, yeah, Friday at 5 p.m., we're going to, after the day of meetings and hacking, and like I mentioned, this is like a whole new thing, so that's what we're adjusting. But Friday at 5 p.m., we're going to reconvene here after the day to have the state of X.Org talk that we have every year. And then we'll be followed by recaps of short lightning talks of every meeting or workshop that happened during the day. And we'll close it off that way. Of course, I have to mention it every year because we pride ourselves on it, but the X.Org Foundation does have a code of conduct and an anti-harassment policy that we're sticking to, and we have to remind everyone, and you've all signed up and confirmed you would abide by it by registering. So just a reminder that the policy is still there. We have a team in place again to report any breaches, so if anything, see something that shouldn't be taking place, don't hesitate to report it to one of those 4 people there, including myself, and we'll address it as soon as possible. It's super important for us that everyone has a very enjoyable experience and that they don't encounter any issues. All right. Once again, Wi-Fi code in case you don't have it. And it's right there, and it's listed out in the lobby too, so you can find it as well. And yeah, thanks again for coming this week. If you have any questions, don't hesitate to come say hello. I'm one of the 2 guys with the long beards here. The other one knows who he is. So you can find me. And yeah, we're good to go. So let's get XDC started. I think our first talk is Connor. So Connor, come right up. Thank you.
Hello, I'm Connor Habit, and this is my talk on ray tracing for Adreno GPUs on Turnip, which I implemented this year. First, we need the obligatory background slide on what is ray tracing. I'm sure a lot of you know this already, but I'm sure that also a lot of you don't. So we need to go through some of this before we can understand what I'm talking about with how this is implemented on Qualcomm and how I implemented it in Turnip. All right, so the point of all 3D graphics, the thing that we're all here for, is to estimate how much light from a light source reaches a given pixel on the camera, which is what this diagram that I stole from someone else is trying to show. The naive way of doing that is to just take a bunch of rays from the light source, bounce them everywhere, see how many hit. That's totally impractical. So the first order approximation, the thing that's actually usable is to work backwards from the light source, from the camera. So we shoot a ray from the camera backwards, see what it intersects, and then keep going and going, doing secondary rays until we hit the light source. This is taken up pretty a while ago for non-real-time use cases, but recently it's become possible to do this sort of more accurate model with real-time use cases by accelerating on the GPU. This is like your standard, the pseudocode of that. This is this sort of idea in pseudocode. The thing to note here is that you have to loop over each pixel and each object, which is going to be impractical for real-world use cases, but it's also very flexible. We can define an object in shader code. As long as you know how to intersect it with the ray, then we can draw it. All right, so now let's talk about some of the problems with this and how this actually works in real-world APIs like Vulkan ray tracing. So real-world ray tracers use what's called an acceleration structure to speed up that intersection, that double loop, by basically quickly skipping irrelevant parts of the scene to quickly find the actual object that that ray intersects with. So this is what the pseudocode looks like with an acceleration structure. We only build the acceleration structure once per frame, and then we query it for each intersection that we want to find. The acceleration structure is only going to intersect some of the objects. For others, it's going to know that it's not even possible to hit it and skip them. In Vulkan, this acceleration structure is going to be another descriptor. It's just going to be like your sample or your texture or whatever. There's just a different type of descriptor that is the acceleration structure. There are many kinds of acceleration structures, but the one that I'm going to talk about, the one that every GPU vendor actually uses, is called the BVH tree, or bounding volume hierarchy tree. And that looks a bit like this. So as the name implies, it is a hierarchy or a tree of bounding volumes, which are usually axis-aligned bounding boxes. So here I have a simple VVH tree for a scene with just 4 triangles. In a real scene, there would be millions of triangles, of course, and these 2D little rectangles would actually be 3D boxes. So the left-hand side shows the scene itself. You have your 4 little triangles, and then the bounding boxes. You have the ones that are inside the triangle itself. Then you have the green ones that are 2 triangles, and then finally you have the blue, which is the root bounding box of the entire scene. On the right-hand side, you can see the tree in memory. Yeah, so the circle nodes are what we call internal nodes, and the bottom nodes are the leaf nodes that are the triangles itself. So when we want to traverse this BVH tree, when we find the intersection with array, we have to do a depth first search. So in this example, we would intersect the array with the blue bounding box. Does it intersect? Yes. Traverse it. Intersect it with the two green boxes. Does that intersect? Well, it only intersects one of them, so only visit that part of the tree. Then does it intersect the 2 red ones? Okay, yes, it only intersects one of them, so let's visit only that part of the tree. So we've skipped testing most of the triangles. We only need to check the yellow triangle. And that is more or less how intersection works. One nuance with this is that in the case where multiple children are being intersected, if we find an intersection with a triangle, we don't have to check anything after it. We don't need to check anything geometry that's behind the triangle. So we want to intersect the closest child first so that we have the best chance of finding an early intersection so that we can then not like visit the rest of this. And I'll come back to this later. All right. There's one more thing to say about acceleration structures because that's not complex enough already. Vulkan makes it even more complex. So real scenes contain both some static geometry, like this table, and dynamic geometry, like this cup that I'm moving around. And rebuilding the whole acceleration structure for each frame would be kind of expensive and not really necessary. So in Vulkan, we split the acceleration structure into what's called the top level and the bottom level acceleration structures. The top level structure contains the whole scene, everything. And then the objects that are at the leaf nodes of that top level acceleration structure are instances of objects. The bottom level acceleration structure contains the object itself. So it would contain like this table or this cup or something like that. And the instances consists of a pointer to the bottom level structure and a transformation matrix that sort of places that object in the scene. So when I want to rebuild the acceleration structure for the next frame, I just change this transformation matrix when I move the cup around, rebuild just the top level structure. Each ray intersection has to walk the top level structure, apply the transformation, and then walk the bottom level structure to find the actual intersection with the triangle. All right. So the second problem that we run into with our naive ray tracer from the beginning is the problem of decoherence. So when we initially send out a bunch of rays from the camera, they're all coherent. They're all roughly in the same direction. They're going to hit the same thing. And that's good for cache coherence. That's good for filling the subgroup and so on. But as we start to scatter them more and more and more, they start to decohere. They go off in sort of different directions. And this causes a lot of problems: bad cache utilization, bad utilization of the subgroups. Subgroups are going to be mostly empty, and we're not going to be running a lot of things at the same time. The solution to this that a lot of vendors use and is sort of accommodated for in Vulkan is called invocation repacking. And the idea is you have a separate shader for each type of object, and then if after all of these bounces, two different things from different subgroups hit the same object, you batch up and you reorder the execution of those shaders. So you execute everything for the merged shader. So in this example, we have two rays that are both in different subgroups. They bounce off, then they merge to hit this object. We would sort of repack them when implementing the intersection with that third object. This is a bit tricky to implement in the driver because it would be very difficult to repack those shaders and then continue off exactly where we left off with the same subgroup with the original shader. So we need to split that shader between the ray trace call and then the stuff that comes after that actually computes the color. And we need to implement basically what's called in the compiler world is continuation passing style. This is an example for like a simple ray of what that transformation looks like. We trace the ray, try to save our state on the stack, and then once it's done, this continuation shader is going to pick up where we left off and then finish the computation. And this is all going to use the same sort of reordering, repacking framework as tracing the secondary ray. So this is done typically in the driver. This is not something that you pass in Vulkan, but there is some affordances in Vulkan and SPIR-V to allow implementations to do this internally. All right, so how is all of this exposed in Vulkan? There are two main ways that you can use ray tracing in Vulkan. The first is the ray query which just implements that acceleration structure thing I talked about and gives you an instruction that lets you intersect array with an acceleration structure. This can be done in any shader. So you can, in theory, create like a actual proper ray tracing thing, but then you have to have one giant Uber shader with all of your materials and so on. Or you can integrate it with the classic pipeline. So you can have your traditional fragment shader, and then inside of that, shoot off a secondary array to figure out an intersection with, say, shadows, or to create an effect of like a glossy object with a reflection. The pipeline extension is the full-throated, we're actually going to do ray tracing, guys, extension. This gives you separate shaders per material and a very complex system of intersecting those with the ray. I'm not going to go fully into it. And this defines sort of a compute shader-like model where you dispatch a grid, and then you can sort of call other shaders from your original shader. All right. Both extensions rely on the acceleration structure extension, which defines the API for how to build an acceleration structure and pass it to the shader via a descriptor. However, the acceleration structure itself is opaque, so you just give it some data. You'd say, okay, go build this acceleration structure, and then it comes back with some opaque handle. All right, so that's the theory. That is how that Vulkan ray tracing extension sort of works. How is this all implemented in hardware using Qualcomm as an example? Because that's the hardware I'm familiar with. That's the driver I work on. I'm going to give you a brief overview of what I discovered this year by reverse engineering the format of the generated acceleration structures and doing tests on the hardware and so on. All right, so what hardware blocks are involved with ray tracing on Vulkan or on Qualcomm? The first, called the RTU, or ray tracing unit, is responsible for intersecting array with a given node in the tree. The driver has to keep track of a stack of which nodes that we visited in order to implement the depth-first search. The hardware just intersects a single node with that ray, which is sort of similar to AMD if you're familiar with that. So by itself, this is only really enough to implement ray query. There's no great way to implement pipelines on top of this. However, starting on A750, there's a new processor called the AQE, which, amongst other things, allows us to implement this whole invocation repacking thing that I talked about, and therefore implement ray tracing pipelines. However, it's not even enabled even on Qualcomm's driver, probably due to performance issues or something like that. So it's still kind of beta. And I certainly have not implemented it yet in Turnip, although I have reverse engineered it. All right, so let's talk about the RTU, the thing that I've actually implemented. The shader instruction that you use with it is relatively simple. I could figure out very quickly. It's mostly taking in the things like the ray origin, the ray direction, everything that's in the Vulkan API, giving it a node to intersect with, and then it returns, this is like the hit distance, this is ID, and so on. In order to understand it, you sort of have to look at the node format first. That is the most complicated part. That's the key. So the format of the BVH node the BVH nodes is much more complex. There are two main type of nodes: internal nodes, which I talked about earlier. Those are the ones that have children in the tree, and those contain the axis-aligned bounding box of their children. And leaf nodes, which are triangles or user-generated geometry with just a bounding box or something like that. All right, so let's talk about internal nodes, which is by far the most complicated part of all of this. So in order to fit the bounding boxes for 8 children in one 64-byte node, Qualcomm sort of had to get a bit creative here, you could say. And you can think about how they got creative in sort of one of two ways. The first way, and the way that I thought of it originally, is that The bounding box coordinates are floating point numbers where the exponent is shared between all of the bounding boxes in a given dimension. So all of the x min and max use the same exponent, all of the y min and max use the same exponent, all of the z min and max use the same exponent. The second way, which is maybe a bit more intuitive, a bit more visual, is to think of a grid in the x, y, and z directions. Those shared exponents define the scale of the grid, and then there's also a grid origin, which contains like a base offset that's added to all of the coordinates. And then each child's bounding box is sort of snapped to that grid. The grid offset, or the mantissa of the floating point number, depending on which way you want to think about it, is 8 bits. So there are basically 256 possible grid lines, and then you snap that bounding box to one of the grid lines. Here's a more sort of visual representation of that, if that was confusing, using the same triangles from earlier. So on the left, we have the grid shown on top of the triangles, and you can see the bounding boxes have been sort of snapped to that grid. And on the right, we have that representation of the BVH tree in memory. The grid, it's not really possible to show on this diagram, but the grid scale has to be a power of 2, and we're really storing the exponent, which is sort of like the exponent of a floating point number. So it turns out that a lot of the complexity of the encoder is that we have to be very careful when we encode this to snap those grid lines by rounding down or rounding up, so that we always expand the box, because it's always allowed to expand things. That just makes things a bit slower. We might intersect an array that we shouldn't have, but it will work out in the end because it won't intersect the triangle. If we did the opposite and made it smaller, well, then things might not work. We might miss an intersection. This turns out to be most of the complexity in the encoder. All right, so one sort of quirk of this is that because we want to fit 8 children in one node, there's only one 32-bit value to identify all the children, which is supposed to be interpreted by the driver as the base index of the children. This is different from other hardware vendors. So the ray intersection instruction returns a bit mask, a 32-bit value, with 8 3-bit things for an array, which is an array of which children was hit, sorted by the hit distance. So we don't have to do that in the driver. The driver, however, has to add that base offset to each of the children to find the actual child node that was hit. All right, so now that's internal nodes. Now let's talk about leaf nodes, which is the other kind of BVH node. So leaf nodes in the bottom level acceleration structure, which I'm calling primitive nodes, contained triangles where the acceleration with a triangle is the intersection with a triangle is accelerated by the RTU, or just an axis-aligned bounding box for those sort of programmable primitives where the shader is going to figure out the intersection. Leaf nodes in the top level acceleration structure, or instance nodes, contain, again, an axis-aligned bounding box and a few extra pieces of metadata to accelerate skipping them in certain cases that are sort of defined by the Vulkan API. Encoding for these is relatively straightforward, except there is a super gnarly, took me forever to figure out, compressed encoding, which allows you to encode up to 4 triangles or bounding boxes in a single node. I won't go into too much detail on this. There is a giant wall of text if you're interested, but it sort of uses delta encoding on the floating point vertices combined with reordering the triangles and reordering the vertices inside the triangle, which has to be done manually by the encoder, in order to store up to 4 triangles or bounding boxes per node. All right, so that's the hardware format. Let's talk about how I implemented all of this in Turnip. So first, this is the situation as it was before. when I started working on this. ANV was the first driver to implement hardware accelerated ray tracing pretty soon after the spec release, which was apparently already 4 years ago. However, on the BVH building side, the GRL language that's used to do that, to string together the various GPU kernels to build a BVH tree on the GPU, was pretty Intel specific and pretty complicated. It wasn't really suitable for sharing with other drivers, for reusing in other drivers. And also, unlike Qualcomm, unlike AMD, Intel does that entire depth-first search traversal in hardware. So it wasn't really, what the lowering for ray queries and ray traversals and so on looked very different. Not really something I could take. That meant that when it came time to do ray tracing in RADV, it was done very differently. Pretty soon after the start, RADV was refactored so that when building a BVH tree, we first create this sort of intermediate representation so that different BVH building methods could be plugged in. It builds this intermediate representation, and then it encodes the intermediate representation into the hardware format. That means that we can switch out different methods of building the BVH tree. Different methods have different trade-offs. So how long does it take to construct the acceleration structure? How efficient is the acceleration structure? How large is the acceleration structure? And sometimes we want to be able to sort of switch those in and out. But as a side effect of that, that means that there was a relatively nice separation between the hardware-independent part, which is building that BVH tree, and the hardware-dependent part, which was encoding it. So and the construction part, building the IR, was using relatively standard Vulkan compute stuff. So when it came time to implement all of this in Turnip, there was really only one thing to do. However, I didn't just want to copy and paste all the code. That would be fun. That would make it very easy. But I wanted to do better. I wanted to create a sort of generic BVH building infrastructure that other drivers, which I know there are a few who have not implemented this yet, could plug into. With Turnip as the first user and RADV hopefully following. This involved a lot of copying things from RADV, obviously, but also some changes like supporting different subgroup sizes, using the generic meta framework for compiling shaders instead of the very RADV specific thing that RADV was doing. There is a bit of a nuance that RADV uses this radix library from Fuchsia that I didn't want to touch, so it doesn't use the generic framework, which I maybe need to fix later. Otherwise, but I otherwise left that unchanged for now. So let's talk about that generic framework. In order to make encoding multiple BVH trees in parallel, because we're going to be building a bunch of bottom-level structures at once, encoding the BVH tree, building and encoding the BVH tree is split into multiple passes, and each pass is run in parallel over all of the trees. So this improves parallelization, reduces pipeline bubbles, but you do need to be aware of it when implementing encoding for your driver. You can't just implement like a single encode function. You have to split it into multiple passes. And the runtime does take care of running the passes for you, but the callback is split between bind pass 1, run pass 1, bind pass 2, run pass 2, and so on. So the one thing to note is that the driver can also choose different encoding methods. So not only do we want to pick different BVH building methods based on user hints, like make the tree as small as possible, build it as fast as possible, we also want to sometimes choose different hardware encoding things, like let's say using that compression for triangle nodes or not using the compression. This is done via encoding keys. So the driver has to provide a callback to choose which encoding key to use for each BVH tree, and then the runtime will sort things based on the key for you, and then you can pick which pipeline to use in your encoding pass based on the encoding key. All right, so the IR itself, which I took from RADV, is relatively straightforward. It exists in the scratch space that the user gives us when we're building the BVH tree. And it has a header, which contains things like the size of the node, the number of nodes, and followed by a list of internal nodes, and then a list of leaf nodes, and then a list of internal nodes. The internal nodes are pretty much the leaf nodes are pretty much what the same data that the user specified in the Vulkan API. The internal nodes just have a list of 2 children, and it's the job of the encoder to then collapse down that tree if you have more children, like 4 for AMD or 8 for Qualcomm. All right, so RADV used a few driver-specific hacks for functionality that arguably should be in the Vulkan spec, but isn't currently. Thankfully, none of these were too difficult to implement in Turnip, but we need to have callbacks for what is essentially a Vulkan extension. In the VK device struct. We have command fill buffer can't take a device address, but the scratch buffer, the user only gives us an address for that. So we have to have an extension to call command fill buffer with a device address. We have this little thing that lets you write immediate data from the command processor, which we use to fill the header and then read it from the shader. We have non-aligned dispatches where you just specify a number of work items and then the last work group can be only partially full, just like in OpenCL. All of these arguably could or should be Vulkan extensions, but for now, we're implementing this via sort of a backdoor in the generic Mesa framework. All right, so one final caveat that I put in, probably because Alyssa would yell at me if I didn't. These various algorithms, in order to work effectively, they need some sort of guarantee of forward progress because they have multiple work groups that kind of communicate with each other. And it's not really possible to efficiently implement building without this. This is also something that arguably could or should be a Vulkan extension. This generic BVH building has been great at exposing weak areas in the Vulkan spec. But in practice, we can just sort of assume it works and hope for the best. So that's BVH building, but there's also the rate traversal part, that using it in the shader. And how does that work in Turnip? Well, it turns out that AMD also works pretty much the same. So there was only one way to go, really, again. So this is heavily based on RADV. Oh, sorry, this is the, BVH building. What else? Again, we have this like top-down algorithm that allows us to fold an internal node into its children, and that's really the most complicated part of encoding. And the other complicated part is this whole internal node business that I was talking about, of compressing them and sort of snapping them to the grid. The other really tricky part is that in Turnip we have to allocate the children contiguously. RADV has some tricks to sort of assume that the children are not, and then reuse the IR locations for things. That doesn't work in Turnip. So we have to allocate the children dynamically using an atomic, and just in each node figure out how many children we want to have, allocate a bit of space with an atomic increment, and then go and encode those children. All right, so that's building the BVH tree. Traversal, also copying and pasting from RADV, my favorite thing to do. All right, this is a absolutely terrifying pile of NUR builder to implement that loop in order to do the depth first search that I was talking about. This really should be OpenCL code because we should be writing it in C. But I think the framework to build all of that isn't quite mature yet. It sort of works, but I would rather copy the stuff from RADV, implement that, and figure out how it works, and then maybe later go and rewrite it properly. This pass has to rewrite this opaque ray query ext structure that defines the result of a partial traversal, turn it into a concrete Turnip specific struct, and it has to keep a stack of the ancestors. Just like RADV, we keep track of only a limited stack of ancestors, and if we overflow that stack, we overwrite the oldest ancestor, and then when we go back up to visit it, we have to find it again and then re-intersect it. Hopefully this happens rarely. There is a bit of a difference that because of this whole array of children thing, there's a different layout of the stack due to the different way that the hardware instruction outputs the list of children to be intersected. All right, so that is the extension that is the Turnip as it exists currently. In terms of future work, well, I have to get it merged first, really. Have a bunch of comments to go over. We just finally landed the last blocker, which was int64 support in Turnip. So now it's finally ready to be merged. Maybe we need to do more performance tuning, and we need to support accelerated updating of BVH trees. There is a thing in the Vulkan spec to allow you to simply re-encode the leaf nodes and then rebuild the tree without having to redecide where all of the structure of the tree, which we haven't implemented yet. We need to support that compression, which is going to be a super fun project, given that even on the blob, it's not even implemented except on the CPU. So trying to implement on the GPU will probably be fun. We need to take a look at the AQE. I've reverse engineered how it works, but I have not implemented it yet in Turnip, so that we can do the ray tracing pipeline extension and get full featured actual ray tracing. This is the code if you want to look it up later. And for RADV, can please someone else port it to use the generic thing, because I cannot do that yet. Did he? Okay, cool. All right, and that's it. So, any questions? I know it's early in the morning and it's very technical talk.
So I'm not sure if this is really a question about your talk or about ray tracing in general, but how do you deal with things like with like more complicated stuff like partially transparent objects, or objects that, or like specular reflections where there's like something that's like a mirror, or even, and this, I know this is a corner case, cases where the wave nature of light and diffraction start becoming relevant.
I'm not an expert in the wave nature of light and diffraction. I'm not sure I can answer that part. In terms of partially opaque objects, there is a notion of a opaque versus partially transparent triangle. And so part of the reason that traversal is not so simple is that you can have a shader that looks at an intersection with a given triangle and returns, I want to keep this versus I don't want to keep this. That way you can look at a texture and say, oh, for this like tree or something, this part is like opaque, this part is not opaque. There isn't any affordance currently, I think, for like multiple intersections, but what you can do is if something's partially transparent, you can return a color and then trace another ray again, like with a higher minimum distance, and then find the next thing. The what?
Do we not have any hit shaders in Vulkan ray tracing these days?
NA shaders? Sorry.
Yeah, so you have first hit and any hit shaders.
Yeah. So that any hit shader is the whole transparency thing where you can return either I hit this triangle or I didn't, and that's for something like trees where you have like just one quad and then you sample a texture to see whether it hit the leaf or not, or something like that.
Right.
Sorry. There one thing for the transparency, it's a bit more complex than that. Like you, for the shader, like any hit and stuff, I don't remember the exact name, but you are not guaranteed to get your intersection in order. So like you still have to do some kind of all order independent transparency, or like do something clever with like multiple ray tracing. Like
it doesn't work for transparent, actually like partially transparent things. It only works for cases where it's either opaque or not, but over the triangle, like parts of the triangle are opaque, parts are not, something like that.
And just like answering the previous one, like for the reflections and specular, it's kind of like naturally for the ray tracing, like there is no complex situation there. I have a couple of questions for the talk. Like, what's the first of all, how does performance compare with the official driver? And second question is, how do I try this stuff? Like, what hardware do I need to have?
So as for the proprietary driver, I need to actually retest that. When I tested it, it was pretty bad. But then Mark told me, hey, the driver does some like performance management thing that we weren't doing in Turnip. So maybe once I re-enable that, it's like one on my to-do list, then it will be better. The performance isn't great now. They implement, for example, compression that we don't, and so on. There's been work recently I did some stuff to make compute faster that probably made this faster. But yeah, that's another thing I need to go back and look into. What was the second question? Sorry.
What hardware?
So it's A740, which again, Qualcomm kind of messed up the names. It's a bit harder to say, but the generation of hardware that's in the Qualcomm laptops has just the ray tracing unit. The generation after that, which is the latest like smartphone generation, has also the AQE, but then it's not really enabled. So yeah, it's like the last two generations, A740 and A750, have this accelerated ray tracing.
Is there like a list of like, okay, this is the cheapest one that I can get to play with it?
Get one of the laptops
Okay.
that came out, the X1E laptops.
Thank you.
Yeah, I have a like detailed question about the encoding.
Sure.
The exponent, is that relative to the previous levels, or is that like kind of freestanding?
It's freestanding. It's an absolute exponent. It's actually, in fact, the same exact encoding as your standard IEEE exponent, which I take advantage of to just pull the exponent from the number and then put it back in there.
Right. That seems very wasteful to me, because you have, if the exponent isn't smaller, for each level isn't smaller than the previous one, then you will encode stuff that is outside of the current level.
Yeah. Well, I guess it's a trade-off of like encoding versus, and also because each the instruction doesn't have any context of what's come before it. It's only intersecting one node at a time, so it doesn't know like what was the size of the previous level. You would have to pass that into the instruction and everything. I don't know. Maybe they'll think of that in the next gen.
I have one question. In terms of number of supported games, how far does ray query get you? Do many games require ray tracing pipeline, or?
Not too many. Well, Crate 2 RTX works, which is of course the critical app. I forgot to take a screenshot to put it in here. Not too many, unfortunately. Because DX only exposed this recently, and you have to expose like ray tracing pipelines too. I haven't gone and double checked. I'm not the app person. Daniel would probably know more, or someone like that.
Thank you.
For AQE, I'm just curious, how does one go about reverse engineering a feature that isn't used by the proprietary driver yet?
Well, it's implemented in firmware. So it's basically reading the firmware. Yeah, so even though it's not enabled, we have the AQE binary. We figured out already the instruction set. I had to write a Ghidra plugin to understand it because it's all compiled from C code. But yeah, you just read that. You just read it. After figuring out this giant mess, like which part of it's ray tracing, which part is it is doing mesh shading, which is another thing that the AQE also does. And then the core line, like the core bit of it, is maybe only 100 lines of C code. So it's actually not that complex. A lot of the details of like how to manage the stack and everything is done in the shader itself. The AQE is just like keeping a list of how many invocations of each shader are outstanding, and then just picking the largest one and then going and executing a compute dispatch. So it's not like that terribly complicated, actually.
How do you reverse engineer a compressed format? Is it a standard compression, or do you have to somehow figure out how they're compressing it?
Pain. Just lots and lots of like throwing things at the encoder, seeing what changes, starting to crawl yourself out of the dark hole. Like, oh, if I change this, I had a lot of hacks to like change a single bit in the floating point number and then see what changed and so on. And then, yeah, sometimes it decides to encode it differently, and then you're like, whoa, everything changed. Let me back up, which turned out to be due to the vertex and triangle reordering thing. So yeah, it's just a lot of like staring at things and like slowly figuring out, oh, this part is what encodes this floating point number. This part encodes that number. Oh, all of a sudden it changed. There must be some bit that controls where it is. Let me look at this other bit that changed as soon as everything changed. Yeah, I don't know. It's a dark art.
You're a legend.
So I noticed you mentioned forward progress guarantees. I think do Qualcomm GPUs actually provide those guarantees? Because I've heard that quite a few GPUs actually don't.
As I said earlier, in practice, just assume it works.
And hope you don't get a bug report.
Yes, I think it does. I'm pretty sure that it does work.
Hi, I have a question about the BVH building. So one of the things that is interesting about this problem is that BVH building, you don't have all the information up front, is what I'm guessing. Like you only get some geometry, you build a BVH, you get more geometry, you update it. Is that?
So you get the whole geometry, even if you're updating it and stuff. So you know the entire object and whatnot. The updating thing is just like, let's provide an entirely new set of data. So you could just rebuild the tree, but we're going to promise that it matches the same layout as the previous thing. So if you want to go and use the previous tree, then you can just rebuild. Then you can just rebuild the nodes and not have redo the encoding and not have to like build the tree again. Yeah, so we do have like a relatively good view of everything when we build the tree. Anyone else?
I know this is a lot of questions, but if nobody else has a question, can you emulate the Ray pipeline extension on top of Ray query?
I knew someone would ask. It would probably, but I don't want to. Because on Qualcomm, we don't even have indirect jumps, or I'm not even sure if we have indirect jumps, which is kind of what you need to emulate it. For example, that's what AMD uses. Because you don't want to put everything into one giant Uber shader. That would cause compilation times to like skyrocket. So you want to be able to compile the different shaders separately and then jump to them. The way that this is implemented with AQE is that you give it a giant list of shaders, and then it sort of picks one and then goes and dispatches it. So each separate shader is a separate compute dispatch. There's nothing to jump from one shader to another shader indirectly, depending upon which material it hit. So yeah, it probably wouldn't go well. All right, anyone else? All right.
Hello, everyone. I'm Mary. So yeah, I work on NDK and Panthros and a lot of things at Corabas since last year. And today we are going to talk about mesh shader on NDK. So first of all, what are mesh shaders? So mesh shaders are part of a new type of graphics pipeline with simplified stage. So you have the mesh shader stage that will generate all your geometry. And that's really closer to the actual compute model because you actually dispatch mesh workgroups. And you can also optionally have a dash shader that allow you to change the size of the subsequent mesh workgroup. So yeah, it's kind of simple. You get a pipeline like that. And let's say we want to do a simple point in the middle of the screen. That will look like that. So you will first set the actual max vertices and max primitives, and inside the shader code, you are actually setting the number of primitives and vertices you are going to use. You set the actual attributes, you set the actual indices for each of those primitives, and that's it. It works like that. There is nice talks from XDC 2022 about that, from Ricardo and also Timur on the AMD side, if you want more reference on that. So, okay, so mesh shader work like that. But like, I want to first mention how you do a draw on NVIDIA hardware in general, because that's going to be important here. So if you do a dump of the command stream on any draw you do on NVIDIA hardware, you'll find something like that. You will first find something that binds the resources from constant buffer attributes, textures, and stuff like that. Then it's going to bind all shader programs for vertices and like each of your stages, actually, and also disable anything that is not being part of your actual draw. Then it's going to set the draw control register with the topology information, the provoking vertex and instance count, I think. And then it's going to call draw vertex array in the command stream. So yeah, it's quite simple. And now I want to mention how it works in the actual shader. So the shader program is actually composed of a shader header and the shader code. So the shader header will contain all the attribute IO and some optimization flags here and there. The access to those attributes will be done with LD and LST instruction in the shader code, and each attribute actually have a unique ID. So if we take a simple vertex shader, you will get, for example, here the point size will be at 6C here with the IST store, and then the position will be after that. So it's quite simple. It's quite elegant, I would say, and it kind of maps to like the traditional way of like doing, the graphics pipeline, I would say. So it's kind of nice. So now let's talk about mesh shaders. So if we do the same exercise, but this time with actually a simple mesh shader, at that point, I'm going to reuse the actual shader from the start. Well, first of all, the command stream. If you dump the command stream, you will get something like that. First, it's going to bind the resources. Then it's going to bind the shader program stages from vertex, tessellation, and sometimes geometry. Then it's going to set the draw control register, and then it's going to call draw vertex array. Okay, so what's going on here? Well, actually, it's going to, when you are going to bind the actual shader stages, it's actually going to set the mesh control register to something, and then set some information about your actual mesh shader. So like everything that you actually define in the mesh shader around the max vertices, the max primitives, and also the topology. And if you actually look at the actual draw part, you will get something like that. So the first thing to note is that the draw control register is going to ignore the actual instance index. And then the second thing to note is that the draw vertex array is actually going to be called with the workgroup size. So what is going on here is that we are actually driving a draw with the input assembler without any inputs, except the vertex ID actually, but let's say without any inputs. So in reality, your pipeline will look like something like that. So if you have a task shader, then the task shader is going to be the vertex shader, and then the mesh shader is going to be the tessellation evaluation shader. And if you don't have a task shader, it's going to actually use the vertex stage for the mesh shader. So that's nice. Now we know how to actually dispatch mesh shaders. But now let's talk about the actual shader code. So I took the actual example from the start, and I can show you like the actual disassembly here. So the first thing to note is that we don't have any LD or AST instruction here. It's using a new shiny instruction, ASB write. So the first thing that you can like actually guess is that the primitive count is stored at offset 0. Yes, offset 0. It's actually written 3, but it's actually storing from 3 to 1, 0 from that space specifically for some reason. Then you can also see that the primitive indices will be after that with that store. And then we have the attributes that are here. So the thing to note here is that we are actually writing directly to the primitive engine internal buffer. So the primitive counts and the primitive indices are stored in one specific space, and then you have the attributes in another space. That attribute space is a bit of madness, I would say, because it's entirely dynamic. It's group, like each actual attribute is grouped with 32 values of the same kind of attributes, so grouped by vertices or per primitives. And the order is defined with the actual shader I/O. So, like for example, if we have the point size that is actually defined and also the position, like position, all the position, then we'll always will have the actual point size and then the position. And if we don't set the actual point size, for example, we will start with the actual position X. And yeah, all that layout actually repeats if you have more than 32 vertices. So yeah, it's really complex. It took me quite a while to figure out. There is here a little example of how that will look like with our shader here if we had, like, for example, more than like 32 vertices. But it gets worse because we have per primitives attributes too. And in that case, the same kind of layout and rule apply, but this time it's going to be after all of that. And the shader header that is going to contain all the attribute I/O information is the geometry stage. And the geometry stage is actually configured to actually pass through all those values directly. So yeah, that's a lot. I implemented all of that, and now I can talk about, like, well, what is the state of all of that? So what is the current state? Last week I did like a little, digging about some demos from Chronos Group. So we have the little triangle working. That's great. We have the double FPS compared to NVIDIA for some reason. I don't know why, but I would like that. But now, let's talk about like just the CTS. So if you run the CTS currently with the merge request I opened some time ago, you will get those results. So like those are the results from last week. It's quite close, but quite far actually, because I currently disable task shaders because task shaders are kind of not in love with mesh shaders. I have multiple issues with them, ranging from the local invocation index being wrong and different, depending if you have mesh and task present. The mesh shader queries are not implemented yet because I need to actually store that in shaders or actually in the command stream, like do that in command stream. And there's probably more here, but that's something for a bit later. The other thing I want to mention is that we don't have real shared memory with the graphics pipeline on the hardware. Because of all of that, we are using the actual internal space to store the shared memory, and that means I need to emulate atomics because I don't have any ways to do atomics. So I'm using the uniform atomics path that does a lot of it, but I still need to handle the atomic exchange, for example, intrinsic. The really elephant in the room now is around the invocation. Because we are running on the actual graphics pipeline, we only have 32 local invocation. The spec actually require 128 of them. And so NVIDIA actually implement that by emulating invocation. So like one hardware invocation can be up to 4 actual invocation in the shader. That's non-trivial to actually like create, I would say. And I had a lot of trouble trying to get that in here to fit. So yeah, I think that's it. I may have spoke a bit fast. Sorry about that. Any question?
If nobody else is going to go, I'm just going to say that you were very much understandable.
Okay, thank you.
exactly is missing for task shaders? Sorry.
Yeah.
So what exactly is missing for task shaders?
Well, task shaders should be working. The thing is, because of all the local invocation mess, I didn't do much testing here, and like all of the faults I'm having right now are probably related to me not handling correctly, having more invocation. So like right now, the way I handle invocation is by just grabbing the shaders and executing that up to full time without while ignoring all barriers for now. So like that's completely wrong. Somehow that passed like a lot of the CTS in mesh shader mode only. But yeah, I know that like the global invocation index is kind of broken, but like shared memory and task payload actually work. Like I know that interaction on both stage work, like simple example work fine. I'm just not sure what is currently broken. Probably I need to set some registers for like unlocking probably more shared memory if needed, like more ASB space for that. But like because of all the local invocation thing, and because I was doing most of my testing with CTS, it's kind of hard to get, make a sense of what is broken on both. Yeah.
So, hey, little dumb question, but
Yeah.
so the disassembly code you were showing as part of the shader program, those are in NVIDIA's instruction, like
Yeah.
not whatever OS assembly would be, correct?
Yeah,
okay.
It's actually using the actual disassembler from CUDA that's shipped with CUDA.
Thank you.
Yeah. And while I'm at it, I can mention that like all the command stream that I showed to are using one of the tool I have made a while ago that allow you to basically hook inside the process the actual doorbell that handle the user submission. And so we basically can dump anything on the command stream that way by just loading a library and getting it that way. Yeah.
For the, you mentioned handling of the greater than 32 invocation mesh shaders that NVIDIA does something to put them all into 32. Is that just like a loop over for invocations or something?
So like the way I'm currently doing it, well, the way I'm currently doing it is by basically grabbing the entry points, making it like a new function with an argument that is the actual local invocation index, and then calling that up to 4 times, and then like just inlining that. That doesn't, that's not correct because you need to respect barriers, but like respecting barriers, like emulating that properly is kind of complicated, I would say. We had some discussion with Faith around that, and I tried to implement that a lot, but I was like having a lot of trouble trying to extract part of the neologic while like staying inside the actual limitation of cutting a part of the logic and like pasting it somewhere else. Like it's kind of hard, I would say. I think I have a branch somewhere.
Can I have a general question? Like when you're looking at the reversing the NVIDIA behavior, can you see their like instruction stream, command stream, and how is that different from the NVK and like method drivers in general?
Like seeing like how to do this, like how to grab the stream and stuff?
Not exactly how to grab it, but like example, you're running some test, right, for this behavior on an official driver. Can you see like everything that the driver is doing, like all the commands, all the shader stuff? And
so if let's say I want to debug, for example, the difference between a CTS test I have and NVIDIA driver, I would say, I have I have on vhooks, that is my library to do dumping of command stream. So if you preload that in the process, it's going to actually dump all the command stream somewhere. For the actual shader part, though, it needs another thing that that is like a layer, like a Vulkan layer that hijack the pipeline cache and then dump the pipeline cache, and then we extract that, like we extract the shader from the pipeline cache. We can also do that for if you have shader objects. I also have a tool that is able to grab the blob and be able to extract the actual like header encode of the shader that way. So like it's not really like a one tool handling everything. Like I cannot do that like simply, but like I have to script that handle both and then extract everything when I run, for example, the test of the CTS or any demo application, to be honest. But yeah, does that respond to your question?
Yeah, thank you. That's interesting. And like the second part of the question is how NVIDIA behavior is different from NVK. Like, is there substantial differences in how things are done?
I mean, that's kind of well, from the top of my head, right now we don't use the multi-view hardware, I would say, for example. We don't use the same way to do draws. Like I did show the actual draw control register and the vertex array thing, but like there is another way that is the old way that we still use. I think I have a merge request open. But like, yeah, there is like a lot of difference here and there because we don't know any, like all the part of the hardware. And so, yeah, it really depends, to be honest. And to be honest, like for example, for the local invocation thing, I'm more and more thinking about doing it with a compute shader and then not doing it that way because I think we still have limitation on the primitive counts that we can emit per mesh stage. So yeah,
So it's a bit different. Okay.
Yeah, it's a bit. I mean, it's kind of different. Yeah.
Got it. Thank you.
Okay.
Daniel Almeida. I work for Collabora, and today we're going to be talking a little bit about porting the new image library to Rust. The new image library is a part of NVK. It's the part that's converting from VK image to actual device addresses and device-specific commands. And another title that I have for this presentation is Rewrite It in Rust. A rewrite it in Rust strategy that actually works. And we'll see why this is the case in a couple of minutes. For the agenda, we're first going to start with some initial considerations of when is it easy versus when it's not easy for you to basically introduce Rust to your project. Then what makes it a component? What makes a component a good candidate to be ported to Rust? After that, we'll be talking about the actual porting process. How does this look like? The memory management side of things, we'll see that there's some corner cases in there that we have to pay attention to. And lastly, how do we debug this? So to start with, when is it easy to introduce Rust in your project, right? Assuming that you're starting up from some pre-existing project that has a whole lot of C code already. So basically, if you want to just add a Rust binary, that will be relatively easy. If you somehow already have support to compile Rust files, and you already have Rust files in there, and now you just want to write a library that will link against your pre-existing Rust files, that's also somewhat easy. So in other words, when you have a feature that's been relatively isolated from the rest of the project, that's good. On the other hand, if you have a feature that has not been isolated from the rest of the project, or when you basically want to have code in Rust that you can call from your pre-existing C code, and you have a huge project in C, that's when it's not that easy, but it's still doable. We'll see, right? And to choose a component, hopefully you're going to start with something small, right? Something that exposes a small public API, something that's self-contained. You don't want something that has a whole lot of functions that will be called from a whole lot of different places in your C code base. This is just going to be a mess. You should choose something small with the small public API first. Definitely. And once you choose this component, then you can jump into the actual porting process. I want to highlight the code I've added here on the left-hand side. I have a otherwise regular Rust function that I named only from C. Again, this is just a regular Rust function. The only difference is that it has this no mangle annotation at the top, and it has a certain C, thing before the F and function token. And the idea is that we want this function to be, as the name implies, something that we can call from our pre-existing C code. And in order for this to happen, the first thing we have to do is we have to disable mangling. And the reason why we have to disable mangling is because Rust, like C++ and many other languages, they use mangling as an implementation strategy to basically implement like generic parameters and closures and namespaces and other stuff. It will use the name of the symbol to actually encode all of this information. This is troublesome because you want a one-to-one match between the what you call your function to the actual name that will be the actual object file. Because from C, you basically you don't want to type. This is actually pretty unworkable. This huge name that you're seeing over there. You want the name of the function you write in Rust to be the exact name of the function you'll be calling from C. That's why you need to disable mangling. So you lose access to all of these things, to generics and closures and namespaces for your public API, not for the rest of your code, but for your public Rust API. But that doesn't really matter, because once you translate that to C, C doesn't really understand any of these things anyway, so we're not losing anything. And the external C token is basically to make sure that the machine code that's emitted by the Rust compiler can actually be called from C, right? And it turns out that if you emit this machine code and you tell the linker how to find it, the linker will link against your function, and you'll get a dynamic switch between the two languages at runtime. Nice, right? So now you will have to port your underlying component to Rust. That's on you. I assume you know how to do that. Because here in this talk, we're talking about how to interop things between Rust and C. Right? So you will port your underlying component to Rust. And once you're done, the idea is that you will write your public API as per above, like using this no mingle and X.Org stuff. Right? And once you do that, these functions will be called from, will be able to be called from C. And then you will basically call this function from C at a later point. And now, as I said, we need to make the linker aware, we need to make C aware that these functions exist. And the idea is that you will need a prototype. And that's not something that's specific to porting things to Rust or anything. Even for regular C code, if you want to call a C function from another translation unit, right? You need to have a prototype. If you want to call even a function as defined within this translation unit, if it's defined below where you are, you also need a prototype. So it's no different here. And you can hint type a prototype. You can create your own header file, typing everything by hand if you want to, and it's going to work. But it's not a good idea because things can get out of sync, right? Let's say your function now takes an argument. Over here, this function is trivial because our call me from C function doesn't take any arguments and doesn't return anything. So it's actually trivial for us to just write by hand a C version of that returns 1 and doesn't take any arguments. But as soon as you take arguments, let's say you take a pointer to struct foo, and now in your Rust code you add a field or something along these lines. Now your Rust version may not match your C version of struct foo, and that's where a whole lot of nasty bugs can start to creep in. And you don't want that. Things can get out of sync relatively quickly. It's not a good idea. And the good thing is that there's a tool called cbindgen that can automate this process for us. It can automate the process of generating a header file that we can then just file include in your C code. And as it's a tool, it's a computer tool, it will, every time you run it, it will make sure that things are in sync and, ensure API compatibility. And it works recursively. So the way it works is it will, start looking at your Rust code and see, every time you have a public function with no mingle and the X.Org C tokens, that will, cbindgen will basically write a equivalent C function prototype for that. It will collect all these function prototypes into a header file and give you this header file. And the good thing about it is that it works recursively. So if it sees that your function now takes a pointer to a struct foo, or in Rust terms, a reference to a struct foo, it will be like, wait a moment, what's struct foo? I should generate a equivalent C version for struct foo as well. And the reason why cbindgen can generate an equivalent version is because for each and every type that we want to basically exchange between the two languages, we have to annotate them with revc on the Rust side. And revc basically tells the Rust compiler to lay out this type of memory exactly like a C compiler would, right? And because the default is Rust, which is not stable, and therefore the two languages do not interop, they would not agree on how the type looks like in memory and blah, blah, blah. But if we use this revc annotation on top, then it actually matches, like the layout between Rust and C matches, and this means that we can basically share structures and share our enums between both languages completely fine. So the summary so far, you choose a small self-contained component, you port that to Rust, you ask Rust C to generate the machine code for that. We have a special, annotations for the public API so that C can call this public API. After that, after you call the public API, the code inside of the public API can call other Rust code without extraction without nominal. That's just for the interop layer between the two languages. And after that, you use the cbindgen tool to basically parse the public API and generate a equivalent header file with function prototypes. You include this header file in your C code, and then you can call your public API from your C code, thereby you can interact with the Rust version of your component from your C code. That's the big picture, right? And for memory management, I'm sorry, you have to be a little bit careful because sometimes in Rust they will allocate, and Rust has this idea, this RAII idea, is sort of borrowed from C++, where you basically acquire resources, and at some later time, once the Rust compiler notices that your type is going out of scope, it will place a call to basically free your resources and just call a small job, right? And if your type implements job, I have an example with a vec. A vec is basically a resizable array in Rust, and that will allocate, right? It's equivalent maybe to std vector from some C++, let's put it this way, kind of. And that will allocate, and once Rust sees that this thing is going out of scope, it will attempt to job that. And we have to be a little bit careful in how we're going to basically do the interop between Rust and C here, because now we need to make sure that we have a way to transfer ownership of the vec. I'm just using vec here as a stand-in for any type that allocates, basically, any type that implements job. You basically need to have a way to transfer ownership of this type to C, and then give C a way to transfer ownership back to Rust so that this type can be freed once the C code decides that it doesn't really need that object anymore. And again, here I have an example for vecs. You can disassemble the vec. You basically will, pass to C the pointer, the size, and the capacity, and you will have this mem_forget call. This mem_forget call will just tell the Rust compiler, hey, please do not include a call to drop here, because otherwise the vector would be freed, and we would be dealing with uninitialized memory from the C side. We don't want that. So we use this mem_forget call to say, hey, we're transferring the ownership of this vec to the C side. Please don't touch this from the Rust side for now. Do not free this, from the Rust side for now. And the idea is that we also provide this foo-less destroy thing, which will take, again, the pointer, the size, and the capacity that we previously made available to the C side. We'll take that back from C, and then we will reassemble the vec. And then at this point, when the vec is reassembled, it will go out of scope and it will get dropped, thereby the memory will get freed. And that's how we will give C a way to basically free the memory once it's done with it. There's no cookie cutter solution. You have to find a way to, disassemble your type and transfer ownership to C, and then reassemble your type back in Rust so that we can free it, basically. And I told you that for all types you want to interrupt between the two languages, you have to have this ref-C annotation. That's actually not true, right? The truth is you can have non-ref-C types, right? If your type is not ref-C, then it becomes opaque to C, right? You cannot, the C part of your code will not be able to access any of the fields or anything. It'll only be able to access your type via a pointer, right? And this is good and bad. It's good because, from one end, you get to have more complex types, which are not ref-C most of the time, like vec is not ref-C. Maps are not ref-C. Most containers in Rust are not ref-C. Most of the types in the standard library are not ref-C. So you get access to these things. But the bad thing is that now you need to heap allocate these types. You need to have them behind pointers. You need to add this pointer interaction, so they have to live on the heap. And there's a good part to it and a bad part to it. And here I have an example of a struct foo, which only has an integer within it. And we have 4 functions. We have a function that creates this foo struct. We have this foo struct will, by the way, be reference counted so that we can have multiple references at different points. It will have a mutex inside so that if you're accessing this thing from different threads, we can do so in a thread-safe manner by locking this mutex. And the idea is that we will provide C with these 2 functions. So get and put. Get and put will increment and decrement the ref count, and then the do stuff will basically, this is just a stand-in for functions that would actually do some interesting work. Our do stuff will basically reassemble the reference counter pointer, and then lock the mutex, and then increment the integer inside. That's how it works between the C and the Rust version. And once C decrements the ref count and the ref count goes to 0, it will get dropped by the Rust side, basically. And that's how the header file looks like. It's basically, we get a prototype for the 4 functions. This view text foo thing is opaque type. You can only, it's forward declared. You can only interact with it through pointers. And basically, the new function, you get a pointer from it, and then you pass these pointers to get input and do stuff. That's how it works. And now, going back to Mule one last time, because once you understand how the process looks like in general, I think it becomes pretty clear on how I made this work with Mule. I had basically the two implementations side by side. I ported it to Rust, and I had basically the C implementation and the Rust implementation side by side. So every time I, let's say this in the example here, I have Mule image init. I now also have Mule as image new, which also creates a image, but now using a Rust component. These two things are operating side by side. And the idea is that I had these asserts everywhere. So basically, every time I had a version in C and a version in Rust, like a function called in C, a function called in Rust, I would assert like some things to make sure that the two versions matched along, each path where the component was being called. Where the C component was being called, I would add a call to the Rust component and assert that the two data structures were a perfect match between the two, let's say. And at first, the asserts were obviously hitting, triggering all the time, but after debugging this for a while, they did not trigger anymore. And that's when I knew that we could remove the C version and have only the Rust version, and we could also drop this RS stuff from the name of our function and basically remove the C version completely. And this is upstream. This is already working for a couple of months now, and this is the overall strategy. And the idea is that you can take this strategy and you can apply the strategy easily to other components in C projects like Mesa, so long as, again, you identify a somehow self-contained piece of the code base that you want to apply the strategy to. I think that's a strategy that can scale for the project. That's a strategy that's been used, like, let's say, in Firefox and other projects as well, to slowly port them to Rust. And that was what I had to say to you guys today. Thank you for hiring, and see you next time. Bye bye.
Hey. You can see us fine. Anyone has questions? Hopefully that wasn't too confusing. Any questions, please come to the raise microphone. Oh my God, that's for mine it works. Oh, good question. There we go.
So you mentioned you can create a Rust definition in the header file and use a tool to generate the C header file. But if you're using Rust to re-implement an existing library and you want to make sure your match, you ideally want to use the C header file. Is there a way to generate a Rust header file from a C header file, or include the C header file in Rust instead of doing it the other way around, to make sure you have the same types as you did before?
If you can do it the other way around. So what I did was to be really real careful thing down, and then I asked cbind to generate it and then compare manually. That's what I did. I have no idea whether you can do it the other way around. I'd say that you probably can't, to be honest.
Oh, that seems very unfortunate. It seems like the language.
Yeah.
I think you might be able to by having the C, by including, at least for function prototypes, by including both in the same C source C file, and then the C compiler will, if you have different prototypes of the same function, the C compiler will complain.
Yeah, I could. Yeah, I have no idea. I didn't try this, so yeah.
There's actually a tool called BindGen which does the opposite direction. You take a C header and it's generating your Rust definitions. So that's possible and works.
Yeah, I'm aware of. Yes.
Quick question. For the mutex full example, is there a specific reason why it's returning result by pointer, but not by function result?
If it's returning a result by point, what do you mean?
Because you're passing a pointer to where it will write the return value, but the function itself doesn't return anything.
For the new function?
Mutex full example.
Yeah, but when you say you're passing a pointer, are you referring to the new function that is assigning a pointer, the one that takes a dual pointer?
No, it's. Can you show the slide, or it's? It wasn't the video, yeah. So you're creating a mutex object there, but you're not returning it by value from the function. You're passing the pointer where it will be written as a function argument. Why is that?
No, I don't think there's any reason. I think you can do it both ways if you want to.
Okay, so it's just an example. Thank you.
One more?
Is it possible to access non-RepRC Rust data types from C, or at least avoid the extra allocation by manually passing the right size of and offsets if necessary, so that C knows how much to allocate, even if it's not. And then just if you want to access a field using manual pointer arithmetic?
Well, the usual thing to do with non-RepC types, again, is to treat them as opaque. I guess you could poke in there if you are inclined, but again, as the type, as the type is non-RepC, I don't think you can actually know where exactly you're indexing with it, the data, right, within the memory. So, so your question was, can you repeat the question just to make sure I answered that properly?
So could you, so even non-RepC types, and I guess there's also rep-packed, which is also a defined layout, but for types with an unspecified layout, Rust, there is still a known size. You just have to ask the Rust compiler for it. So could you pass that to something and say allocate this much memory, and then the Rust side writes to that much memory? Or would that just be overly complex in the cases you've dealt with?
Yeah, I don't think this helps anything. I mean, ideally, because the opaque thing is also very convenient, because for the mutex example, I'd say like Rust doesn't know anything about Rust's mutex, so it doesn't really. There's no point in poking there for whatever reason. And also, I mean, I think it's convenient to have Rust in charge of the allocation and deallocation instead of trying to push that to C somehow. So yes, I think even if we could do what you're suggesting, I think that's a little bit counterproductive. That's at least my opinion.
Hi, thank you for your talk. I'm wondering high level, so I can understand the advantage of, say, writing new code in Rust, but are you finding it advantageous, or what advantages are you finding of porting old code that already exists in C to Rust?
Can you repeat the rest of the question? What
advantages are you finding from porting existing C code to Rust?
You know what I like about porting, existing stuff to Rust is that we can be more expressive using the type system and stuff. We also can use the Rust standard library, which again I think is gives you a little bit more of expressiveness maybe. So I mean, ideally you want to basically start from scratch, but that's not realistic, So I guess that what I'm talking about here is that you take what you can get, right? It's not as good as starting over from scratch, but you still get to have some of the things that Rust will provide you again as the type system and the use of the standard library and blah blah blah. I think that in particular, if you're writing Rust code, it's good that if you're taking a reference, let's say, you know that this reference is valid, so you don't have to basically worry about taking a pointer and then this pointer being null, that type of stuff. So I think it helps you basically weed out these types of errors. That's where I think the advantage is.
Okay, thank you.
All right.
Yeah, we're out of time.
Yeah. Thank you, Daniel.
Hi, my name is Liud, and I am going to be presenting on RVKMS and KMS drivers in Rust. So mainly what I'll be talking about is a general overview of RVKMS and the bindings we have so far, and also sort of an honest opinion on what I think of Rust and why I kind of think it's a game changer for the kernel. And I won't be talking about memory safety, but we'll get into that in a little bit. How did this start? The main thing was we've been working on a new NVIDIA kernel driver, Nova. And Nova is written in Rust particularly because NVIDIA's GSP firmware doesn't have a stable ABI, and trying to handle this in C is pretty hard. We got the inspiration from Asahi, who uses a very similar approach to handle unstable ABIs with their firmware. And we also think that through upstreaming Rust drivers, we can prove Rust's readiness, and projects like Asahi can end up having an easier time being able to upstream their work. So, of course, device bring up for a new driver is pretty difficult, and it takes quite a lot of time. And we also have to be able to write all the Rust bindings that we actually need to get the kernel driver running. Luckily, a lot of this has already been done in RVKMS or in Asahi. So there's a lot of bindings we can reuse, and we really just have to work on, upstreaming them and figuring out the things that need to be changed. Surprisingly, though, one of the notable exceptions of this was kernel mode setting. Asahi's kernel mode setting driver is pretty much one of the only parts of the driver that's actually written in C. So there's not any pre-existing KMS bindings for us to actually write a driver against. Nova's way too early in development to be able to have a KMS driver written for it. So, but like KMS was a large enough surface that we wanted to be able to work on this sooner than later, and ideally in parallel to the rest of Nova. So we decided while Nova was getting ready that I would try to port a KMS driver into Rust to try to come up with a set of bindings. And we ended up choosing VKMS because it's a pretty simple driver. It doesn't require any specific hardware. And yeah, it's so quick explanation of what VKMS is. It's a virtual KMS driver, meaning it pretends to be a display device. It's also capable of CRC generation, and it also supports write-back connectors. So RVKMS, of course, is the Rust port of the VKMS driver. It's very early in development driver-wise, doesn't do a whole ton yet. Basically, all it really does is register a KMS driver and set up VBlank emulation using high-resolution timers in the kernel. Eventually, we're going to have CRC generation, hopefully, along with connector write-back. But despite all of this, and despite it being very early in development, it's been very useful in making progress with these bindings, and I think we've actually come a pretty long way in that regard. I also did my best when working on these to sort of structure the API around not just VKMS's needs, but also what I've seen from other drivers like i915 and Nuvo. But I would definitely say a lot more time went into the bindings than the actual RVKMS driver, of course. It's pretty small at this point. But yeah, it's worked pretty well. So my main goal with the KMS bindings was, of course, prevent undefined behavior or safe code, of course. Make incorrect KMS API implementations nearly impossible. Rust gives us a lot of tools to actually be able to prove that the way things are implemented are correct at compile time. And we wanted to take advantage of this, but also make sure that we're ergonomic, right? We want to make sure we protect from mistakes, but we don't want to make code messier, inflexible, or more difficult to write. And also as well, one of the things that sort of was brought up by Seema is trying to make sure we limit conditional handling only where it's needed and only where it really makes sense, since that's a big part of the ergonomic issue. So one of the things that sort of brought up is the ability to subclass objects. We'll talk about a little bit what that means shortly. And outside of this, we also wanted to make sure that we only really supported atomic. We'll probably have some basic support for the various legacy helpers. that provide compatibility APIs for user space applications still using legacy mode setting. But yeah, it's atomic only, and we don't really want new legacy mode setting drivers. So these bindings work on top of the DRM bindings from Asahi and Danilo. Additionally, there's quite a number of other dependencies, but there are quite a lot of differences with RKMS bindings versus in C. For instance, unlike in C, RKMS bindings are mostly in control of the order of operations during device registration. And we provide basically a single trait that a driver will actually implement in order to support KMS. And that sort of handles calling things in the right order, registering the device, and that sort of thing. This trait currently has two main parts: mode config info, which basically fills various static information in the mode config structure. This is stuff like the minimum, maximum resolution, various cursor capabilities, and etc. And then create objects, which basically gives you access to a special unregistered KMS device type. This type allows creation of static mode objects like CRTCs, planes, that sort of thing, and non-static mode objects such as connectors can also be created here. In the future, we'll probably add hooks for customizing what happens during the initial mode set. This would normally be used for things like reading back hardware state. So if you want to do fast set, you turn on your computer and it doesn't do a mode set when you get to the login screen. But since we're a virtual driver, we don't really have any state to read back. So for the time being, we just kind of call DRM mode config reset and reset the whole display state to being blank. So one of the neat things is drivers implementing the KMS trait get a KMS driver trait implemented automatically. And this is nice because it actually lets us make it so that KMS-specific methods are only available to devices that actually implement KMS. This is really advantageous because it basically allows us to, from all of our bindings, assume KMS is set up and always there, instead of having to handle, runtime checking, like did they set up v-blanking or did they set up this specific feature. We're able to do most of this at compile time. And of course, that avoids returning quite a lot of options in places where they might not necessarily make sense. So the first part of this is mode objects. DRM sort of has a concept of a mode object where it's basically a object that is exposed to user space through an object ID. It might have a ref count, but it might not, and it can be created at any time. Ones without ref counts can only really be made before registration, though. They also have properties, but we haven't really gotten there in the RVKMS quite yet, so not going to really go over that very much. For implementing these, we have a mode object trait, which for ref counted objects, it's pretty easy. Ref counting fits pretty nicely with Rust's lifetime requirements, and we provide a trait that these objects can use to basically reuse the same kind of like mode setting reference infrastructure that all the other objects are using, since it's basically the same for all of them. Static objects, on the other hand, are a bit more challenging. So static objects will typically share the lifetime of a device, which is not easy to directly map to a lifetime in Rust. A lot of objects are like this, like CRTCs, planes, and encoders. But to work around this, we provide the static mode object trait and something called a KMS ref. Basically, KMS ref acts as a reference count on the parent device while providing access to the static mode object. So it basically fulfills Rust's lifetime requirements and allows owned objects of references to static mode objects. We may eventually replace this with Danilo's DevRes type in the future, but that is currently unclear quite yet, or right at the moment. So implementing things like planes, CRTCs, etc. was a bit more complicated than one might expect. Very few drivers use these structures unmodified. You might recall that I mentioned subclassing, and this is sort of where this comes into play. because more often these objects are embedded within driver private structures. For instance, with VKMS, we have VKMS CRTC, which implements a DRM CRTC. Usually, these additional structures contain various driver state, private driver state. So this can be display state that might need to be tracked outside of a single atomic commit. It might also be static driver information, like port capability or capabilities, port mappings, and so forth. As well, a lot of drivers often will have more than one subclass of an object. Both I915 and Nouveau are pretty good examples of this. So you might have different classes, for instance, different types of connectors, different types of encoders, and so forth. So luckily, this is not the first time we've had to do something like this in the kernel of Rust. Asahi actually had to do something quite similar for gem bindings. In gem infrastructure, this sort of thing is also very common, where there might be driver private data that you have to keep with an actual gem object. So luckily, it was a little less variable than KMS, since KMS kind of does subclassing a lot harder, but it was still a very good one starting point for actually getting this working. So on the actual Rust side, this is done with a number of traits: driver plane, driver CRTC, etc. And a driver is allowed to have multiple implementations of these traits, so to be able to handle multiple different subclasses. Driver data can be stored in them in two ways. The first is being able to pass immutable data to each object's constructor. So if a device has to do some sort of dynamic probing as it's loading, you're able to actually pass whatever information that you need into the structure via that entry point. And then, of course, the other point is send sync containers. So this is basically just any kind of thread-safe lock, a mutex, a spin lock, etc. So in KMS drivers written in C, drivers will typically switch between a common representation and a subclass representation. So this goes sort of back to the DRM CRTC and VKMS CRTC thing we mentioned before. There's a couple of reasons for this. Sometimes you have operations that you want to apply to all different mode objects, regardless of type or only specific types and so forth. In order to handle this, we have two different types of interfaces, a fully typed interface and a opaque interface. And we do the same thing for atomic states as well. And the idea is that you can sort of switch between these two types at runtime. So if you don't need access to driver-specific data, you would use an opaque type. Otherwise, you'd convert it to a fully typed connector. This is done fallibly at runtime. We do have some infallible conversion operators that you can use if you have a simpler driver where you only have like a single implementation. But yeah, this also required us to actually add something so that we could get consistent vtable memory locations, which is not something that Rust has by default. Constants are basically treated more as inline constants rather than actual static constants. But luckily, thanks to some of the work that's been going on, we actually have a macro for implementing this now. So the one thing that's not entirely figured out here yet is if a driver needs further classing. For instance, I915 has more granular subclassing when it comes to a lot of its mode objects. Things like Intel connector are sort of like an upper level representation of an object, whereas you would have like Intel HDMI, Intel DP, and that sort of thing to sort of represent the different types of connectors that you would have. And occasionally you want to be able to go through, you know, in various hooks to work on specific subclasses like that. So I'm hoping this will be pretty easy to just do through Rust's trait system, but it's still sort of to be determined at this point. Now, then we get to atomic commits. Things diverge a bit when we get here because Rust's data aliasing rules say that you can only have one of these at any given time, infinite immutable references or only one mutable reference. So if every atomic check, update, and so forth callback only affected the given object in question, this would be pretty easy. But a lot of times this isn't really the case. A lot of drivers will iterate through the state of other objects in their atomic callback, not just the object that the callback actually belongs to. So I originally tried implementing this using just references, but it worked out pretty poorly. A good example is, let's say you're in an atomic check for a plane, and you want basically to go through other objects in the atomic state overall. You already have a mutable reference to the plane state, which means that that plane state is taking a mutable reference from the atomic state. But how do you iterate through other objects then? You've already taken an immutable reference, and you can't really take another. And you can't take an immutable reference either, of course. So the second time through, I decided to take some inspiration from RefCell. This is a Rust API for handling situations where the data aliasing rules aren't exactly ideal. Immutable and mutable borrows still exist, and they sort of have the same rules, but they're checked at runtime instead of compile time. And this also means you're actually able to use them through immutable references, which we use here. So basically, for the atomic state, you're usually working with it through a container called an atomic state mutator. And basically, you always have immutable references to this container, but this container sort of handles doing the bookkeeping at runtime and handing out borrows of atomic states that you want to modify or inspect. So you can only have one borrow for each state at a time, but you can take out multiple different state borrows at the same time, which ends up covering most of the cases that we would actually want to cover. Borrowing is fallible, but we're still able to make this pretty ergonomic. So for instance, atomic check callbacks will pass a pre-borrowed copy to the new state, for instance, so that you don't have to borrow a new one. And we'll also be implementing iterators as well that allow you to iterate through various unborrowed states in the actual atomic state. This works pretty well because most drivers, if they are modifying other objects in a specific objects like atomic check or atomic commit, so forth, they're going to be iterating over other object states. So the types that we use for this are borrowed CRTC state, like borrowed plane state, and so forth. And these have the same sort of separation where they can be used with fully typed states, or they can be used with opaque states. So this brings us to the atomic commit composer. Basically, actually that's supposed to say atomic state composer, but basically this is supposed to be a wrapper around a atomic commit mutator. It represents an atomic state that hasn't finished the atomic check phase. And it's basically the same thing, but it also allows you to add new objects into the atomic state. So we can actually restrict adding new objects to only happen within atomic check callbacks where it makes sense. And this can also, in theory, easily be used for allowing drivers to perform arbitrary commits in kernel. So basically, you would be able to create an atomic state, take out a composer and use it to do something, for instance, like enabling CRCs, where you might have to do an atomic commit in order to actually turn them on. So then we also have high-level commit callbacks. There's only a few of these so far, but the main example is atomic commit tail. These have some pretty interesting constraints, because for one, there's certain orders of operation that you can put in these that wouldn't make sense, that you don't want. For instance, CRTCs can't really be enabled in a commit before they're disabled in that same commit, because physically that doesn't make sense. Because a commit's only supposed to do basically one state change at a time. And we have to ensure that the state as well can't be mutated once it's made visible outside of the commit context. So this is the point where a driver calls commit hardware done. And this is sort of on us, because DRM doesn't really know the state of borrows. It can't tell if we have a mutable borrow of a state taken out once we call atomic commit or commit hardware done. So we have to handle all this on the Rust side. And breaking any of these requirements would result in undefined behavior, which we don't really want. But luckily, this comes up with a really cool feature of Rust, type state patterns. These aren't entirely unique to Rust, but they're not typically common in other languages, and Rust generally makes it a lot easier to work with than other languages. This sort of allows us to encode the runtime state of something into compile time state. We've already actually used two here, for instance, the atomic state composer and the atomic state mutator. There are the correct names, okay. But we also have unregistered KMS device, which eventually gets translated to device. And basically the idea is you're representing an object at every portion of its lifetime as a different type. And this allows us to have a very powerful tool for actually enforcing API correctness, which sort of brings us back to the atomic commit tail. This is basically another atomic state wrapper like the atomic state mutator and atomic state composer, but it is basically one that you have to implement yourself if you want to override it. And it lets you control in which order commits happen. And we're actually able to do this safely while being able to enforce some of the more complicated requirements that I had mentioned before. Most of this is done using tokens, where we have a token that represents each step of the process. And in order to get to the next step of the process, you have to provide that token in order to prove that you've performed necessary operations. Some examples that we have here are, for instance, with committing mode set enables and disables. You have to call commit mode sets disables, which gives you a ready token. Then you go to the enables, where you pass basically that disables committed token to prove that you passed that step. And then you get a token enables committed token that you can pass later on to that third point there, commit hardware done. And same thing happens with plane updates, where you get a token that says you can perform the updates now. You get a token once you perform them, and you take both of these tokens and you actually provide them to commit hardware done to basically prove that you've performed all of those steps. Now, this can be trivially expanded, of course, for more fine-grained control, because many drivers may have to control the specific order in which certain CRTC commits are performed, or certain plane updates, etc. And it shouldn't be too hard to actually expand it to allow for this. But what's cool about this is it lets you make it impossible to write an incomplete atomic commit tail that actually compiles. You have to perform every step, and you have to perform them in the correct order, otherwise your code just doesn't compile. And every step also takes a mutable reference to the atomic commit tail, which means that if you were to have to take out a atomic state composer, or atomic state mutator, you wouldn't be able to mix it with those steps or cause changes to happen until you've actually performed those changes and no longer have other mutable borrows of the atomic commit tail object, which is pretty nice because it allows us to make sure we're still enforcing Rust's data aliasing tools without rules without necessarily limiting what you can do with them. So optional driver features are sort of the next part of this. KMS drivers have quite a lot of features that are optional. A really good example of this is VBlanks. Everything uses VBlanks to some extent, but not all hardware actually has a VBlank interrupt. And sometimes it needs to actually be emulated by the DRM core. So can we gate these features just like we do with KMS driver? Like, for instance, make it so that if your driver supports hardware VBlank interrupts, you're able to call those methods related to hardware VBlank interrupts, but not otherwise if you don't have support for that. And turns out we can do this. We just add more traits. So VBlank support is pretty much the example for this. If you have a driver where you support hardware VBlank interrupts, you basically just implement this trait on a driver CRTC, and it will expose all of those methods by automatically implementing the driver CRTC v blank trait, and so forth. And we can expand this same pattern to any optional piece of functionality, basically. And since we already control the driver initialization and registration process, it's pretty trivial for us to handle without the user having to do it themselves. So, of course, not much to go over here. You implement the traits, you get the support, and so forth. I'm going to go into the next part of the presentation, but real quick, I want to give a special thanks to the Asahi project, because a huge amount of our work depends on their bindings. Myra Canal, because they also committed quite a few bindings that our driver takes advantage of as well. And of course, also my coworkers, Daniello, and everyone else who has been working on the Nova KMS driver, like Dave Arley, and so forth. But yeah, so my experience with Rust. I sort of want to go over this. First to say, I won't be talking about memory safety. I think one of the big mistakes a lot of people make when they're trying to advocate for Rust is focusing entirely on memory safety. The thing is, we kind of all know that C is unsafe, that it's a problem, and that it's sort of a problem that's inherent to C. I think a lot of times what people don't realize is when you focus on this point too much, you sort of come across as talking down to a lot of kernel developers, because we kind of already know this. And it was honestly a reason that I had actually avoided touching Rust for quite a while. But so if you want to hear more convincing arguments that aren't really centered around this, this part is definitely for you. So yeah, the first thing I sort of noticed is Rust can be a kernel maintainer. Maintainers don't scale, and being a huge part of being a maintainer is trying to stop bad patterns in code. This is pretty time consuming though. It requires you to re-explain yourself repeatedly and hope you didn't miss something. It can make you snippy, can burn through your motivation, and of course that depends on what kind of contributors you work with, but it's certainly a problem. Rust can help here though, because the thing is, Rust can give us a lot of tools that allows us to enforce things that we would have had to have done over email ourselves. And this is something that is a lot more capable than anything we were really ever able to do in C. So type state patterns like the atomic commit tail are a really good example of this. A lot of times they have little, usually no runtime cost. And the thing is, the upfront cost in sort of figuring this out is large, because there's a pretty big learning curve and you sort of have to really rethink how you write a lot of your code. But the potential for this saving time long term is kind of astounding. Of course, a lot of people wonder, what about unsafe code? But in my experience, this doesn't end up changing things very much. A lot of the time, even with unsafe code, for one, unsafe code actually sort of also acts as an enforcement tool, because if you have something that the compiler isn't able to actually type or check itself, you're able to write what's called a safety contract. And if you try to do unsafe code without providing a safety comment, the compiler will actually complain at you. So you're sort of forcing people to actually write down the logic that they're following when they're doing something that might violate the invariance of the language. And this is really useful because it gives maintainers and reviewers something to actually look over to verify whether what the person is doing is making sense. And it's sort of wild what the end result of this is. Because in writing RVKMS, I spent almost no real time on debugging. I think I could probably say I spent only around like 24 hours total, and this was work over the course of a couple of months. So it's kind of impressive, because almost every time I've written a driver, it's sort of gone like this. You write a bunch of changes that make sense and are sound, but then you end up spending the next day, sometimes even multiple days, debugging subtle errors all over the place. Maybe you forgot to check something for null, maybe you forgot to initialize something, maybe you forgot to make sure that something was thread safe, And this process sort of repeats itself as you're writing a driver in C. But over Rust, it kind of doesn't. If things compile, a lot of times it will actually work, which is a very weird concept, and it's almost unbelievable until you've actually dealt with it yourself. So before I worked with Rust, I was kind of off-put by a lot of the patterns that you would see. Things like not having null, for instance. Like, oh, I have to handle both conditions every time? What if I know something's not going to be null? And tons of types? That sounds kind of like a nightmare. But Rust is ergonomic enough that you almost barely think about this stuff a lot of the time once you've actually finished designing your bindings. And not even that, it also almost feels obvious what the right design is a lot of the time. Just about every construct that Rust is forcing you to deal with, it has almost a million different shortcuts for actually making it as legible and simple as possible. And a lot of the time you're not even, like, once you're past the actual stage of developing bindings or APIs and so forth, you're not even really thinking about this stuff afterwards. A lot of the time the language just sort of handles it for you. I think as well too, something that's nice to mention is the scope's a lot smaller than it seems. I see a lot of people make comparisons, you know, C++ versus Rust, but I don't really like these because Rust is kind of a shockingly small language. It definitely is complicated to wrap your head around at first, but you can certainly tell the scope is pretty limited. Whereas a lot of languages like C++, you know, they're okay, but a lot of times they feel more like a framework than a language. And a lot of the stdlib sort of comes from the same KISS philosophy that C standard libraries tried to do, but it's continually being iterated on, not in a way that makes it difficult to maintain compatibility per se, but like in a way that actually just makes things easier to work with and less troublesome. And a lot of times too, what this leads to is there's usually not a whole ton of different ways to actually do something in this language. So once you actually get used to Rust, the correct way of doing stuff almost always feels obvious. So that sort of leaves me with one last question. Would you rather repeat yourself in a mailing list a million times to stop people from making the same mistakes in their code using your mail client, or would you just rather have the compiler do it? So give Rust a try. So any questions?
Hi. On the topic of Rust as a maintainer, how do you see Rust's role as API evolves, where you have more than one correct way of doing things?
Do you mean like Rust's API or
No,
what?
the API of DRM evolves, right?
Yeah, honestly, I think it's not too difficult to work with. I have found that refactoring Rust code tends to be very easy, even with a lot of more, like subtly more complicated changes than you might have to work around in C. There's still obviously some overhead there. It's not free, but like I think more often than not, a lot of times it's not too difficult to actually fix things later on. Of course, obviously the goal is to avoid that, but yeah, I think it works generally just as well as C would for that sort of thing.
No, the question is on if the API for DRM changes, where you have different ways that are both correct. You said some of the code doesn't even compile nowadays if you don't do all the stuff.
Oh, yeah, I mean, so the point of that is mostly like, because the thing is, it doesn't compile if you take all the steps, but we're limiting that to a subset of steps that make sense for any driver, regardless of use case.
Yes.
And most of this is sort of things that we already have as requirements. So it's not necessarily that we're like limiting if a driver needs to take extra steps, because the way I tried to design all of this is so that we can expand upon it in the future. Like, for instance, with having to control the order of operations in which you might have to update CRTCs is a pretty good example. It's not something we support now, but actually adding support for it and still maintaining that sort of compile time checking is actually pretty simple. It just sort of means being careful when you actually make those APIs to make sure, you know, that you leave room for things to actually be added in the future without necessarily constraining people and stopping them from being able to do that.
Okay, thanks.
In working on the Rust bindings, were there like a number of cases where it was beneficial to the C code because you found things in doing the work that was, you know, broken in C, and would thus be having Rust equivalent of a lot of the C code would make the C code better just by being another way to check it?
Definitely. Actually, I feel like I got a little lucky here because for the most part, DRM is surprisingly well defined, but it sort of became obvious that exactly what you said, sort of using it as a tool to verify C code is correct. I definitely run into this in other areas of the kernel where you would find certain areas where, for instance, you realize, oh, there's no locking here. They just sort of rely on, say, you know, driver initialization being a single threaded context or that sort of thing. So I definitely think it's a very useful tool towards that goal, because it does definitely sort of force you to actually sit down and codify all of these things. And it very obviously points out like things where this was never actually codified and we sort of in C just managed to avoid it running into problems. But yeah, we definitely ran into that a few times.
Apologies if the question won't make much sense. I'm only briefly familiar with the stuff that you talked about, and I didn't understand half of the talk. And but the question is like, it seems that you've been struggling a lot with the like current, you're limited by the current drivers, like APIs and data models that they have, and the Rust kind of by its structure imposes certain limitation of what you can and can't do. And I wonder, have you thought about like, if you could ideally, like it's not practical obviously, just completely not think about what current drivers do, and how would you design the whole like DRM stuff from scratch given the like Rust requirements?
A little bit, but I've sort of found, and that was sort of what I was getting at before with DRM being well defined, that like surprisingly, even though some of this was challenging to sort of figure out the bindings for, I didn't run into a whole ton of situations, actually pretty much ever, where something was actually impossible. And a lot of this is sort of helped by the fact that like DRM is pretty well documented, especially in terms of like locking and that sort of thing, and most of the cases where you would typically run into problems in other parts of the kernel. So I feel like that hasn't necessarily been necessary, mainly because of the care that was taken with a lot of DRM. So yeah.
Thank you.
No problem.
Interesting talk, and I need to get a bit more into Rust and learn more, but in your opinion, I've seen a lot of talk about Rust for like sort of new components or things that are disjointed from existing code. But does it make sense at all for like features that one would add to DRM, like the color pipeline API, for example, now that's blowing up on Xavier's desktop with null pointers that I haven't seen with my IGT tests, but I haven't done enough end-to-end tests. Would it make sense to do that, or would it be a lot of overhead and creating bindings, etc.?
I actually think it would, because I mean, I think the thing is, even though, like, the main difference is Rust forces you to think about this stuff up front before you can really get something working. So at first, a lot of the time, it seems like, oh, wow, this is a lot of work and overhead, and I'd rather just sit down and do this in C, right? But, like, a lot of the time, the things that Rust is forcing you to think about upfront are things you're going to eventually have to think about anyway. And the advantage of actually doing all of this stuff upfront is that once you actually manage to come up with something that it looks like where it would actually work, it usually does. And you end up spending more time sort of figuring out the actual hard design problems than you actually do, you know, chasing down all the references or that sort of thing. So I think it'd actually be a pretty big help if we were able to get bindings generally far enough that we would actually have the infrastructure to be able to implement support for that sort of thing.
So pretty much it forces you to be a bit more honest up front rather than say, it works, and deal with it later.
Exactly, yeah. I think the one challenge would be figuring out how we can extend that to drivers written in C, because unfortunately the one thing that is a little difficult is actually interfacing with Rust code from the C side. But I think that's something we might be able to do in the future, or yeah. But I definitely do think it is a generally good idea.
Thanks.
No problem.
Right, I have one about object lifetimes, which is kind of adjacent to memory management, which proposed not to talk about. But to preface this, my KMS is a bit rusty. As you know, it's been 5 years since I worked on KMS side of things in DRM. But I have a vague recollection of some object lifetimes being non-composable. The borrow checker being quite a big constraint on how you handle lifetimes. How does that work when one sub-object has to outlive its, enclosing scope?
That was mainly what the static mode object stuff was for, because that was actually one of the big challenges that we ran into, where what usually ends up happening is the way that you deal with it is everything maps to some sort of lifetime. Sometimes it's not necessarily lifetime of the object you're working with, but for instance, with static mode objects, the closest lifetime we could map to was the one for the device.
Right.
So a lot of times you just sort of have to trace that path because everything's going to have some sort of lifetime, and it's sort of just figuring out how to map that to a specific resource and sort of make that work in a way where, it's basically pretend ref counting, where you're taking a ref count of something else in order to keep the object alive. And that seems to actually work pretty well.
Right, so you force it back into a composable structure, basically.
Pretty much, yeah. And for objects where, that's sort of where the type state patterns come in as well, for, objects that you can only really compose early on in the driver initialization process. You can sort of use having different types of devices and that sort of thing to constrain it there so that you don't really have to worry about that later on.
Right. Thanks.
No problem.
I had sort of a more specific follow-on question to the question earlier about where if you started from a blank slate, could you get a better design? Are you happy with the ref cell design you came up with to handle all the borrows and stuff you couldn't work out with the atomic state objects, or do you think if you started from a blank slate, you could move that back up to compile time and make it a little cleaner?
I actually think I am pretty happy with it. It's a little bit of a shame that we have to do some of that at runtime, but a lot of that really just comes down to maintaining a single bit mask of objects that you've taken out. So I think overall it actually works surprisingly well. So I'd actually say I'm pretty happy with it.
So if you're not experienced with either Rust or KMS drivers, you probably still want to start with C to get something working. What do you think?
For the time being, I would say probably yes, but that certainly might change in the future. The only reason I really say so right now to start off in C is mainly the issue of bindings not being there. Because pretty much every time I've had to add some sort of feature to RVKMS, it's been, okay, now I have to write these bindings as well, which usually doesn't just mean knowing Rust or C, but also having a pretty deep understanding of how a lot of lifetimes and synchronization in DRM actually works. So I think if you're just starting off from scratch, right now it's probably better to do it in C, but that certainly might change in the future as this becomes more fleshed out.
Thank you.
Apologies. Quick question. How are you happy with Rust compile lifetimes regarding to kernel level projects? Because usually like with bigger projects outside of kernel, it's like I'm very unhappy about it.
You mean Rust like in terms of like borrow lifetimes?
No. I mean like compile time, like how much time it takes to compile.
Gotcha. Actually surprisingly happy with it. But I will say I feel like it's a little too early for us to really tell. As we get more drivers written in Rust, I think that's really when we're going to start to figure out how difficult the compile time is, because it may certainly get larger or longer as we actually add more code.
Thank you.
Thank you.
Hi, my name is Alex, and my topic today is color operation for Linux color pipelines on AMD devices. And the agenda includes a brief overview of the color pipeline API and the DRM color operations we define and implemented for AMD devices. And finally, an IGT KMS color up test that demonstrate the color pipeline API and the color operations. So what's a color pipeline API? So this was presented by Harry previously, but let me just do a recap. So it's a model prescribe a recipe for how to manipulate pixel values to arrive at the desired outcome. And it's an API to allow user space to discover the hardware capability in a more generic way. And the individual DRM color object will be changed via the next property of the DRM color up to constitute a color pipeline. And as you can see on the screen, the color pipeline is attached to the DRM plan, and on the right is just a dummy example how a pipeline and the color operation can be. So we defined 6 color operations for the AMD devices. The 1D curve and the 1D lot is for the degamma, shaper, and the blender transfer functions. And we also have the CTM, 3x4 matrix multiplier, and the 3D lot for HDR. So what's see on the screen on the bottom is a color pipeline for AMD device. And on the right is an implementation in the AMD GPU. And there is you can see there is a one-to-one mapping. So the degamma transfer function will map to the 1D curve. And the HDR multiplier will map to the multiplier color up on the right. And so is the 3x4 matrix and the shaper and so on.
So I'll give some brief discussion on each of the color ops we defined. So the first one is the 1D curve. So a 1D curve is applied to all the color channels. And because we are basically just passing a number for the predefined function, so it just have a one field called 1D, curve 1D type, which is enum values. And for now, we define 6 1D curve, which is the sRGB EOTF, BT2020 OETF, and the PQ125, and plus their inverse functions. And the 1D log is pretty similar to the 1D curve, but it provides a way to pass a custom 1D log from the user space to the Linux kernel. And because we are passing a lot, so we do need a size. Let's define the number of the lot entries, and also a data block. They will be where the user space write the lot itself to. And the reason to have a 1D lot is because the 1D lot is provide more flexibility than the 1D curve, so people can use whatever they want. And the CTN 3x4 color up, or as the name suggested, it passes a 3x4 matrix. And because the 3x4 matrix has a fixed in size, so we don't need a size entry. We just need a place, a data block that we can write the 3x4 matrix from the user space. And similarly to the multiplier, it's a simple multiplier that apply to the all color values. And it's 64 bits in length, and it's in the format of S31.32. And the final one will be a 3D lot. A 3D lot has it's more complicated, so it has 3 fields. Like the first one will be a list of the supported mode, and a 3D mode basically describes the 3D lot itself, the format of the 3D lot. And because the hardware can support multiple different modes, so we have to return a list of the 3D modes. The second is the mode index. Basically, it's index pointing to a 3D mode that selected by the user space. And finally, the data. The data itself is a data block for the 3D lot that user space will write to. And because we need to describe what the 3D lot looks like, we also need to define 6 fields for the 3D lot mode. The first will be the lot size, which can be any size, such as the 9, 17, or 33. So in our example, we are using the 17. And the second one is the lot stride, which is the stride for each dimension of the 3D lot. The reason to have this stride is mostly it can extend the length of the table. So it's mainly used for the purpose of the memory alignments. And the third one will be the interpolation algorithm for the 3D lot. And for what we are using the tetrahedron. And the color depths can be 8, 10, and 12. And the color format is specified the 4cc values. So it can be, for example, XRGB 16 or XBGR16. And this, of course, also depend on the color depth above. So if you are using temp 8 bits, you can just using the XRGB 8. And finally, is the transverse order for when passing and writing the 3D lot. So basically, what it means is the XYZ axis of the 3D lot. So it can be, for example, lot 3D, RGB, then will be the X will be R, and Y will be G, and Z will be the B, or it could be BGR. So that depends on what you are trying to use. And this is just an example of how we handle the color up in the AMD GPU DM. So as you can see, there is a one-to-one mapping from the left, like which is the color pipeline, and how we handle each of the color pipeline on color objects on the right. And because not all color up are to be used, so you can actually set a bypass for each color up. And the bypass can be set independently, but could be depending on the hardware as well. And finally, the IGT KMS color up is a test for testing each or multiple color ups. Because we have quite a few subtests in the color up test, but they are behaving in a similar manner. So for all of the subtests, like basically take an input image, like the one shows on the screen, and the test will generate two outputs. One is the hardware output, which it will read back from the write back, and the second will be the software output, which will be using the same color transformation, but done in the CPU. If the output image are the same or similar, then a subtest passes. And we also allow some margin of errors. I believe it's like 5%. Just because some of the, for example, the 3D lab might not be they might be not one-to-one map. So there could be some of error margins. And this is the format of a subtest. So basically, you do have each subtest you have a color format followed by one or more color operations. The format could be like, for example, 10 bits or 8 bits, and the color up will be like one of the defined one previously. So for example, if we have a subtest for the gamma test only. So, and we are using 10 bits, and that will be the first on the button. So XR30 and the sRGB EOTF. If you do need to do more testing, do a test for multiple color ups. For example, if you are going to do 3 1D curve, then you basically just append the 2 other color ups at the end of the test. And the IGT test will execute the sRGB EOTF for the gamma, and the invert EOTF for the shaper, and the sRGB EOTF for the blend. And for now, we have all of the color up tested in IGT. So you basically can have like 8 bits that's on the left and 10 bits that's on the right. They include the 1D curve and the 1D lot, 3x4 matrix, multiplier, and the 1 3D lot as well. What's shown on the screen is a struct for the 3D lot in IGT. So on the top is the 3D lot that will be passed from IGT to the kernel. And the middle is the 3D lot mode that describes the 3D lot. In this example, we have a lot size, so that means we are passing a 17 by 17 by 17 3D lots. And the interpolation will be the tetrahedral and so on. And on the bottom is a function that we are using for CPU to compute the same software image, and then we can compare the two, just like I said before. So what you are seeing on the screen right now is the workflow between the IGT and the Linux kernel for the 3D lot. So first, the IGT will initiate a game mode, where the Linux kernel will return a list of the supported mode by the hardware or by the driver. Then the IGT will match is in the one I just showed, like will match its mode, and the particular one that has that have the exact match, and then you will write the index that pointing to the mode, and the 3-step complete the mode selections, and the IGT is now can write the 3D LUT followed by the frame buffer, and then you can read back the frame buffer from the write back, and then you will take the output and compare the one we also compute from the by the CPU. So the two images will be compared and generate a pass and fail. Yeah, and so that's pretty much everything. So both of the Linux kernel patches and IGT patches are sent to the mailing list. So if you want more detail, you can also check out the mailing list as well. Yeah, so that's about my presentation. Any questions?
Hi, is any of this available to call through DRM so that a compositor or something like that could implement any of this hardware features?
Yeah, I think so. Yeah, they are called by the DRM.
Okay. A second question. I have actually a little bit of experience implementing some of this. So I am a W-rich contributor, and one of the things that one of my recent contributions is implementing software for transforms. So 3D LUT, like you were talking about, where you have a 3D texture and you just map a color in and you get another color out.
Yes.
So one of the things there, one of the benefits of doing it in software, not on the CPU but as a GPU shader, is that you only need to recompute the color transform for the damaged regions of the screen. So if you only have a window that's in a corner, you only have to, in software, you can only recompute the color transform for that corner. But the problem is with hardware, does that computation happen every time the screen scans out? Is there some sort of way that actually software using a GPU shader would be faster than using hardware if depending on the screen size that is changed?
I think it's always done. There is no. Oh, yeah, Harry.
Yeah, just some comments. It doesn't matter because this is fixed function hardware. The pixels go through the pipe no matter what. Powering on the 3D LUT takes a bit of extra power, but once it's powered on, the pixels will just flow through, and it doesn't matter. Like it's always the entire thing. Pretty much, right? We're not using a shader to compute it in hardware. We're using fixed function hardware. That's why that's where the benefit comes in. You can leave the graphics portion off, and that can save you a lot of power.
Okay, and one last question. Some of these 3D LUTs can actually be quite large because it's the 3D. Yes. It's in 3D. So if you increment one dimension, you allocate a lot more space. Suppose you already had an allocation through Vulkan or whatever for the memory. Is there some way to reuse that memory for the fixed hardware, or you have to send DRM, a pointer on the CPU?
So for now, I believe you have to always send it. But in the future, as long as the hardware is supported, we can create another color up that support passing the 3D LUT by reference. Yeah, it's definitely possible with the interface, but not right now, not in the current implementation.
Okay, thank you.
Hi, thanks for the interesting talk. I just had a quick question about the KMS color op test. So how are you doing the comparison between the write back output and the software buffer?
Sorry, by the one captured from the write back. So that would be the output from the hardware, and we take the output, the input image, and do the same computation by the CPU, by the software, and generate another one, and we do the comparison between the two.
Yeah, so I was just wondering how the comparison is done. Is this via the existing FNV1A CRC helper?
Well, basically we compare pixel by pixel, but with the range of margin, could be 5%, I believe, or something. So nothing fancy, just the value comparison.
Got it.
Yeah, and a brief comment on the CRC portion of your question. The reason why we're doing pixel by pixel comparison is because hardware and some of these algorithms might have off by ones. As soon as you're off by one, your CRC is wrong. You don't know if you're close or if you're far and get complete garbage, right? And to understand whether you're close, you really have to look pixel by pixel. Are they within a small amount of margin?
Yeah, thank you.
Got it. Thank you.
Quick question. Is there any, maybe, or unless I missed it, is there any work on the testing of the blending of multiple hardware layers in this path? Or is there actually support for hardware layers in this on this hardware? What's the
blending of the multiple planes, you mean?
Yeah, you would have different planes with different color space that goes out with a certain color space, yeah.
That's a good question.
Okay. Well,
no tests for that yet. No. One could create tests for that using IGT, using the same approach. You could just, Control-C, Control-V, the existing test, create your two planes and get your write back and compare that to a software model of the same thing. I think what you're getting at is, right, how is blending done and, how do we define what
it's a very desktop thing, right?
Sorry?
It's a very desktop thing to blend.
Yeah, I mean, it's an important question. Right. We haven't created tests for it. Somebody could if they wanted to. It's an important thing to look at.
Thank you.
Thank you.
To be fair, if you test the correctness of each plane, the blending is hardware specific anyway.
The question is loaded. There's many decision and trade-off that you're gonna do in the middleman between your input, the blending engine, whatever it is on your hardware, and the final output. So you can do the full mathematical perfect operation where you go back to very high depth linear representation, or you can cut corners.
But the reason this API is defined as a prescriptive model is so user space, like a compositor, can understand what's happening, right? The way a compositor programs this pipeline, they should know whether they will be, for example, in linear space for blending or in PQ space or in some extended sRGB or normal sRGB space, etc., right? You could model this directly through GPU shaders and then do the same through your display hardware. And at the end of the day, the display driver doesn't know the blending space. It just knows I need to do this and this and this to my pixel. Then I'll blend them together and then, I do something else.
I'll just add one. Is EGT planning to add support for external acquisition for the case where hardware where you wouldn't have actually a write back connector?
It's not done yet. I mean, theoretically you can do that. I know Google has put some convenience that you can capture the output, but it's not. You can do that, but it's not done yet.
Yeah, there's Chameleon being dispatched in some of the labs now. Yeah. Okay. Thanks.
Thank you. Any other question?
Which compositors do you expect will actually use this color pipeline, and under what circumstances would there be a color transformation to actually do? And also for the stuff that really cares about color accuracy, will the fixed function be good enough, or will they have to use shaders anyway for precision reasons?
So I already have an implementation for Quinn where we can right now in full screen only, once we have more overlay plane usage, whenever we scan out a video, for example. About color accuracy, if you want accuracy, you don't want to use that at all, pretty much, because the results are just slightly different from more exact calculations that you do in a shader.
Okay, so like movie studios and such will just be doing everything in shaders.
Probably.
But this is, so what kind of color changes would Quinn be doing?
For example, if you have an HDR video but an SDR screen, we can do tone mapping with a 3D lookup table, or change the gamut of the video, change the transfer function, those sort of things.
I think it's important to understand that this is mostly for the playback of content, not for the production of content. And why it matters is because most of people uses a battery to playback. And this is where you actually save on power.
Oh.
Okay, thank you, everybody.
I work in the Turnip team, and today I have the pleasure to talk about the new backend compiler for here is a quick overview what I'll be covering into this presentation. First, we will start with the motivation behind the project, why I started it, and what problems I'm aiming to solve. Next, I will talk about the status quo, when the project started. After that, I will introduce the target instruction set architecture. We will then move on to the road to success and look at the progress I have made, the milestones achieved, and how the project has evolved over the past few weeks. Following that, I will share some shader debugging techniques I've been using, which have been crucial to track down issues and validating the implementation. I will then outline some of the challenges faced during the development and how I overcome them. Finally, I will wrap up with further work discussing what's next for the project and the remaining areas that need to be improved. Let's get started. Motivation. The current compiler, or let's call it near translator for Ethernet, is less than optimal regarding its architecture. It uses near for register allocation, breaks new validation, is hard to follow, and takes too much of my time when the bigger new effective set. For me, it's not that fun to work with. I want a grown-up compiler. There are many ready-to-use new passes that are a lot easier to work with if there is a backend IR and a real backend compiler. Sure, it might be possible to do the same with the kernels, but that needs a lot of time. I think in the long run, memory-safe programming languages will become more and more important through the whole graphics stack. Rust is just one of them. As Mesa gains more and more components that are written in Rust, I think following that trend is a good thing. Rust helps to write efficient and safe code. Everybody hopefully knows this. For me as a developer, Rust offers some other really nice things. There is a need for an external unit testing framework like G-Test. And another heavily discussed topic is code style. Rust FMT makes my life a lot easier, so I really do not need to care about code style at all. I write my code and let Rust FMT do its magic. Let's have a look at the initial situation. First, there are a lot of good resources for learning about compilers and compilers in it. Many talks and blog posts show how to write a good compiler and how to use it for OpenGL and Vulkan. I recommend visiting planet.predesktop.org and the XDC YouTube channel. You'll find a lot of helpful content from the community. And last year's XDC, I already talked about new backend compiler. Looking back, it was a good first step, but was stopped by some missing ESO-spec bits. The good news is I can reuse many of the new passes I wrote back then, so not much time was wasted. As I always wanted to have a good foundation to build a compiler on top, I needed much more unit testing. I wanted to take a random but meaningful encoded instruction from the binary block, disassemble it, compare the result with the expected string, and be able to take that text representation, assemble it, and compare it with the initial test data. This gives me the confidence that ESO-spec is completely enough. As a waste product, there is an assembler CLI that can be used when somebody wants to replace shader binaries, for instance. The best part about the new assembly bib is that it is written in Rust. It uses the best library for parsing and procedural macros to work directly with the EaserSpec XML file. It makes it easy to add new instructions or bits by simply updating the XML file. When I was working on the proof of concept compiler, I spoke to some user-driven maintainers to see which programming language they preferred for the new compiler. Most suggested modern C++ or Rust over C. At that time, the new project was still in its early days. Now, after several months, NAC has made a lot of progress and done all the hard work of proving Rust can be used for backend compilers in the Mesa. But there is no shared Rust code for compilers. This isn't a problem, but it means that someone might want to work on that. As a refresher, let's talk about the target user of pre-advanced GPUs. My target instruction set architecture uses a fixed size of 128 bits for each instruction. It supports up to 3 source operands. The ISA is a VEC4 based one. There are 3 different encodings: the default encoding, the extended instruction encoding, and the enhanced vision instruction set. We have 2 types of registers: temporary registers and uniform registers. Temporary registers are used for general operations, while uniform registers are more static, storing values that don't change during shared execution. Some temporary registers might contain fixed input or output data semantics. It also supports inline immediate values, which means we can put small constant values directly into the encoded instruction. As I told you, all of this is defined in etnaviv.xml file using EaserSpec. Let's have a look at the sample instruction from the target instruction set. This instruction was randomly chosen, but it shows a lot of features I talked about. First, it uses 3 different types of source operands: a temporary register, T0, an immediate value, 32, and a uniform register, U0. It is also using the U32 instruction type, meaning it's working with 32-bit unsigned integers. Let's talk about how I got started with this project. While working on the assembler, I really enjoyed using Rust. So I decided to try building another Rust-based compiler. I came up with my master plan. Reuse the near passes from my previous proof of concept backend compiler and take all the reusable paths from now. The goal was to write enough code to be able to compile a very simple shader. Getting it to run on the actual GPU would be a challenge for it. I decided to target OpenCL because it was very little state to worry about, supports many arithmetic instructions and data types. This way, I could just focus on the compiler itself. By lowering operations in NIR, I can take advantage of NIR's optimized sets, which do all the hard work for me, and I do not repeat the same optimizers in my backend compiler. NIR is also so flexible that it allows hardware-specific in-strings and makes the life really easy for compiler development. After translating from NIR to the backend IR, there's usually some extra cleanup to do. That's why I wanted to include some basic optimizations from the start, like copy propagation and dead code elimination. By the way, these are the only optimization passes I currently have written in Rust. With this, I can transform near already quite well to fit my target pizza. Supporting control flow like loops and conditionals was a priority from the beginning. Fortunately, I could reuse NUX generic control flow graph implementation, which saved me a lot of time in testing. Also, it's important to support all the hardware bit sizes from the start. Choosing OpenCL helped here a lot. The Adreno backend compiler, or shortly EBC, started about 3 to 4 months ago. This time, I'm focusing on building it with a strong foundation and a long-term vision. Instead of rushing to get quick results, I want to ensure that the architecture is solid and flexible enough for future extensions. Let's have a quick look at the past month of work. My biggest wish was to keep it a secret as long as I could. It is another proof of concept which might never enter the final stage and will never be merged into Nisa. So, I started again as the fork of the NUX compiler. As the target instructions and architectures are different, I had to make it back 4 ready and have done many rounds of refactorings. I think I had at least 2 versions of ir.rs before I settled with the kernel one. I do not remember the time it needed to get to the point where I was able to compile a simple OpenCL shader into something that looked okay-ish, but it was less than a week. I had no liveness analysis nor a real list allocator, and that should be the case until quite late in the development process. Lucky me, there are 64 temporary registers I could reuse. In the second stage of development, over the past few weeks, I was focused on refactoring and fixing bugs. During this period, the compiler was able to pass around 200 to 300 piglet tests. It was a small but promising milestone that showed things were moving into the right direction. I also started this discussing the proof of concept with Fate. At this point, the source compiler Rust directory was formed. Fate and me moved the following components into this new folder. We have now an SLI straight, a bitset struct, the control flow graph builder struct, everything to work with new shaders in an immutable way, and a small vec struct. I hope that the memstream layer and the near instruction printing also find its way into common code. I also began having conversations with Carol about OpenCL topics. This helped me identifying some OpenCL specific challenges that the compiler even needs to address. Even though there was progress, I still was uncertain about the proof of concept's future. In the next phase, the number of passing piglet tests started to increase, although progress was slow and required a lot of effort. I managed to reach around 1,000 passing tests, but it came with a lot of frustration. Debugging failures took up most of my time during this period. Despite the difficulties, I continued fixing bugs and adding more unit tests, which eventually increased the number of passing tests to more than 2,500. A major turning point was adding support for live analysis and register application. With these additions, the number of passing piglet tests increased to around 3,000, showing that the compiler was becoming more robust and capable. Also at this time, I started to test the OpenCL CTS3, and I was surprised how much I was testing at that time. So to summarize my road to success, when we look at how I've started and how it is going, I would say the compiler architecture I've chosen works. The optimization path is doing a good job, and all the near lowerings looking fine too. There's still room for improvement for the generated assembly, and there are also still some failing tests, mostly that have problems with the precision of the results. But overall, I'm really, really happy how this ended, or how the current state is. Let's dive into some techniques I used for debugging shaders during the development. The more tests started passing, the bigger and more complex the shaders became, making it harder to debug issues. Thankfully, the compiler supports atomics and basic control flow, and we can use printf debugging in OpenCL. This works right off the box, and that was really helpful. With printf, I could validate that my load instruction were fetching the correct data. It also allowed me to split complex one-liners into multiple steps and check the intermediate results. But at some point, even printf debugging wasn't enough. This is because a single OpenCL instruction can end up generating several GPU instructions, making it hard to track down issues. One of the most important things for me was to understand the flow of data in the shader. I wanted to see the values in the destination registers after each GPU instruction. Since I have a lot of registers available, I thought there must be a way to achieve this. My idea was to re-index all the relevant registers in the backend IR and then add store instruction to every used register and its selected components. This approach allowed me to track how data moves through each step of the shader. It opened up a whole new world of debugging for me. Let's have a look at a simple example to see how this technique works. This is a very simple OpenCL shader example that uses the native square root function in OpenCL. I have chosen the native square root function as it maps directly to nearest FSQRT ALO opcode and is better for presenting on the slides. To make sure this debugging technique works properly, we need to ensure that the global size is set to 1. When we enable this special data flow mechanism, it generates shaders looking like this. This shader includes all the extra store instructions for each register and its components. It stores all the data into a special buffer. After running the OpenCL kernel, we can map and read the buffer object to check the values of the registers and see how the data moves through the shader. When we put all the information onto one slide, we clearly can see the flow. In this example, we have an input of 4, and we get the output of 2 for this square root function. This was just a simple shader to show how the debug mechanism works. I have used this technique successfully on much larger shaders. It might not be a new idea and could have been used by others, but I haven't seen anything like it in Mesa's code base. And it saved me many hours compared to doing manually. As this debug mechanism is not that much code, I am playing with the idea to just ship it. Because I think somebody else might run into some issues and might want to stare at the data flow. Let's talk about some challenges faced during development. During prototyping and the whole development process, I was running into many challenges. First, having two different compilers for one driver seemed manageable at first, but in practice it turned out to be quite tricky. I had to duplicate a lot of codes, especially for meeting uniforms in the command stream. When I had OpenCL image support, I ended in a ublitter call and it needed a compiler too. One thing that took some time in my head was the fact that near is untyped, and my instructions are typed. Even my inline immediate method. First, when I was confronted with this challenge, I started to reconsider some life decisions and took a short break from this whole proof of concept compiler topic. After some days, I came up with crazy ideas how to improve the situation and created some merge requests that luckily never got merged. The feedback I got for these merge requests helped me to deal with my problems, and in the end it worked out. Lastly, I underestimated the amount of reverse engineering still needed. I had to identify new instructions and figure out the extended instruction encoding. Some issues like understanding a single bit in the load instruction took me several days to solve. I found that examining how the same feature behaves in different new generations can be helpful, but it is a slow process. There is still more reverse engineering to do, and I will need to keep refining the ESA model in ESA spec along the way. Besides getting EBC reviewed and merged in its current state, there are a few areas that still need further work. In C, integer promotions refer to a set of rules that define how smaller integer types like char, short, are converted to larger integer types, typically int or unsigned int, during arithmetic operations. The purpose of this promotion is to ensure that the operations are performed using at least the width of the int type, which is usually native word size of the machine, to avoid inefficiencies and unexpected behavior due to type size. You might wonder why this topic is relevant in this context. As I want to write a competitive compiler compared to the binary block, I often compared the assembly of both compilers and came across this topic. You might remember that my target ESA is typed, and almost all other instructions are supporting 8, 16, and 32 bits wide data. I think it's time to look at this one slide. Here we can see a simple kernel that adds two char values. On the bottom, we see the near representation or part of the representation of the shader. And we can also see that we are doing 3 conversions. 2 are going from 8-bit to 32-bit, and 1 is going from 32-bit to 8-bit. And these kind of conversions are not needed, and the binary block compiler do not need them. It just works directly on the 8-bit data type 4600. So there's still room of improvements here. If I want to get the EBC compiler into the ballpark of the binary compiler, I think the easiest way would be to have OpenCL only a near pass that removes all these not needed type conversions. But it's still on my to-do list. I have a proof of concept, tested it a little bit. I even talked to Carol about the idea, and he is in the same boat as me. And it might even help other backend compilers in the DSI, targeting OpenCL. There are several things I'm planning to work on moving forward to expand the capabilities of the compiler. First, I want to extend the usage of shader stages. From experience with the old compiler, this task shouldn't take too much time. And I think this will be one of the first tasks I want to work on after EBC landed. Next, I want to support more GPU generations. The compiler is written with all GPU generations in mind, but it was never tested, and yeah, legalization path is missing. I am currently targeting 1 GPU generation for all my work, and yeah, still need some testing and validation to support the older GPU generations of Vivanti GPUs. And the major long-term goal is to fully replace the older compiler. Right now, both compilers are being used together. I remember OpenCL image support, and that complicates things a lot. Once the new compiler is ready, I plan to phase out the old one, but it will take some time and some major release cycles to get to that point. Another area I'm exploring is building an instruction stress tester like the one from MUX. In etnolib, we have an instruction of code verifier written in C that lives in the etnolib GitHub repository. And I really would love to move this code into Mesa's code base, convert it to Rust, as the compiler is written in Rust. And it should help me to even have more trust in the things we're doing in the compiler and the whole ESA spec definition of the instructions that I created. So, thanks for watching my talk. I hope I could give you a little insight in the development of the etnolib backend compiler. I would break the merge requests for EBC during XDC, and I hope everyone is curious to have a look at it and do code reviews and help me to get this piece of work faster into Mesa than usual. With that, I also want to thank everyone who talked about Rust, near OpenCL, and guided me into the right direction. And thanks for allowing me to ask all these stupid questions. And Carol, sorry if I always come with the same problem. Hey, the binary block compiler does this. Why we aren't doing this? Why is our ear so big? So thanks for your time, for your support. And with that, I think I'm good in time. And it's now time for your questions. Oh, and by the way, if you like to work on these kind of topics, maybe Geiger is the right place for you. So, let's start with the questions.
Any questions? Move up to the microphones.
You mentioned you added register allocation. I'm curious what algorithm you're using.
The simplest one, I'm using the one that is in the util is util folder. So grab column one. Okay, then. How long the video is going?
Okay, we can still hear you. We can still hear you.
Okay, can you hear us? Hello?
Oh.
Okay. It's more of a comment than a question, but just with the integer. Oh. I was hoping to make a comment. Can you hear me?
I think he's having a problem with his web. Maybe Christian, turn off your camera so we can at least have a good sound.
Okay, I can hear nobody.
And I was going to talk about the integer promotions. No.
Just turn off my camera.
Yeah, I guess I can.
Sadly, I can't hear anybody, so I wish you a nice day and thanks for watching my talk.
Integer promotions aren't that exciting anyway.
Can you hear us now?
Hi, I just had a comment on the integer promotions. In my in some previous work I did back in the compile industry, I found those to be really tricky to optimize. So I was wondering about how you were going to approach that, like with things like, even something as simple as calculating a plus b divided by 2. If you do it all in 8-bit, it'll overflow, but if you do the promotions, it won't.
That's correct. But my main goal is always to match what the binary job compiler can do. So hopefully I can figure it out fully to get the rules correct.
Yeah.
But that's a topic I would like to look into.
Yeah, it helps to have a good test suite, so that's great that you're doing that. Thank you.
Thanks.
Any other questions?
All right, I think we're really done for now. Thank you.
That's it, Christian. Thank you very much.
Thank you very much for attending this talk. I'm Chema Casanova, and I'm presenting the enhancements to the Raspberry Pi GPU driver stack. I'm a member of the Gallia graphics team. I'm an open source developer. I worked during the last years on the graphic stack of the Raspberry Pi devices, mainly on the Mesa user space driver and in the optimization of the desktop experience. I'm representing a team. It's not all my work. That would be impossible. That we're working on the Raspberry Pi GPU driver stack. It's composed by Iago Toral, Alejandro Piñeiro, Juan Antonio Suarez, Mayra Canal, and Christopher Michael. So, well, it was 1 year ago at previous SDC in 2023 that the Raspberry Pi 5 was launched in that October. And at the same time, it was launched a new version of the Raspberry Pi OS. That the main highlight was that the desktop was using Wayland for the first time by default. So with this new hardware, the Raspberry Pi is a new evolution from the previous model of Raspberry Pi 4. It's the new generation using the Broadcom video core architecture number 7. It has a higher clock rate than the Raspberry Pi. It allows us to draw up to 8 render targets. That is a requirement to have support for OpenGL Desktop 3.0 and in advance. Has better support for subgroup operations, better instruction level parallelism. And well, at that time, when the hardware was in the market that people could buy it, the drivers in the kernel space and in the user space were already created the merge request and landed at the end of the last year. So, well, the support of the APIs is conformant for OpenGL 3.1, and at that moment was Vulkan 1.2, and nowadays is Vulkan 1.3. And we have enabled at that time the support for OpenGL 3.1, but it's not conformant because some missing features. So, well, I have this table to show the different names of the kernel, driver space, user space. From the first generations of Raspberry Pi, from 1 to 3, they use the GPU from Broadcom, the video core number 4. And the kernel driver is hosted in the kernel module of DRM BC4 that handles the display and the rendering part of the driver. And on the user space side, we have the BC4 driver that supports OpenGL and OpenGL ES. In the Raspberry Pi 4 and 5, we are in two newer generations, the video core 6 and 7, respectively. And in the kernel side, we have the BC4, that is the same display driver that we have for the previous generation, and the B3D, that is the one that is managing the rendering. And on the user space side, now we have 2 drivers, B3D, that is the one for OpenGL and OpenGL ES, and B3DB, that is the one we use for Vulkan. So, well, what happened after a year? Well, we achieved Vulkan 1.3 conformance last August. It was quite recent. That implied exposing 18 new extensions that some of them implied a lot of work. We started taking advantage of the improvements that the Raspberry Pi 5 has in the instruction set related to subgroup operations. So now we can support both valor, shuffle, relative, and quad operation. And at the same time, we had previously only enabled in the compute states, and now there is support for these operations in the fragment states. And well, there were multiple improvements also in the shader compiler backend. This work also implied, as we shared the backend between the Vulkan and the OpenGL driver, the improvements in both of them. This is the list of the extensions that are recently supported. I would like to highlight the implementation of dynamic rendering that was quite interesting and quite hard to implement, and all the work that we did on subgroups that was quite complex on that. On the other part, on the B3D driver, the one that handles the Gallium driver that handles the OpenGL, OpenGL ES, we enabled 7 new extensions, mainly using more of the capabilities that Raspberry Pi 5 has. I highlighting one that is a small and simple extension that is texture barrier that allows you to put a point of synchronization when you are rendering. So the textures after this point, you have guarantee that they have been flashed to the memory, so you can reuse in different places. Because it has improved a lot of the performance that we have perceived in the Raspberry Pi. As I commented before, we cannot support OpenGL 3.1 a conformance version because in Raspberry Pi 4 we don't have support for 8 render targets, but we have in Raspberry Pi 5. That was thing that's solved. Not using too much application, but it's a requirement for the spec. We have not support in the hardware for non-seamless cube math filtering because in OpenGL the hardware is targeted for OpenGL-ES and it only targets the seamless cube math filtering. And we don't have support for the some 16 bits render format targets that are the lunar ones. They are not enabled in the hardware, so we cannot use them. But we support everything else. This has allowed us to. Some applications are going to fail, but now we can run a lot of OpenGL applications that previously were not possible to use that. On the kernel side, we have implemented several things. One of those was announced in last XDC, but this finally landed. This is support of CPU jobs. This has allowed us to avoid stalling in the user space driver when we have some features that didn't have support in the hardware. For example, the hardware cannot support getting a timestamp, so we manage that, obtaining the information, installing the driver, waiting for the job to finish, and then doing another submission. But we stop submitting commands to the GPU in that time. So the CPU jobs delegate that work to the kernel that can schedule that job that is going to be managed independently. And the user space Mesa driver is going to continue doing the submissions without the stalling driver. This has been available since Linux kernel 6.8 and Mesa 24.0. One interesting features that we have recently enabled in the kernel is the support of the super pages capability. The B3D memory management unit supports 64 kilobytes and 1 megabyte pages. These are called big and super pages. So to manage that, we need to create a continuous area of memory. We need to enable the transparent huge pages support in the kernel. And at the end, we are making, for example, 16 4K pages together. And this can be represented with only one page table entry. This allows us to access a part of the memory to only do one lookup for the page entry instead of doing all that use space in the cache. So it seems to be an interesting need. At the same time, now we thinking about if we are have support for big pages or super pages, we can do specific optimization in the user space. With the traces we usually work, we have seen a general improvement of 1.33% in just changing the kernel with support of super pages and without super pages. That is interesting, but we have observed that there is not such a low performance improvement, but it's a big boss in some emulation cases. I'm going to show some videos recorded by my colleague Mayra Canal, that she extracted the ROMs from the PS2 physical copy of the games and ran them on the Ether PS2 emulator. Don't worry, it takes 5 minutes to play the video. So we are going to see the burnout. On the right side, you are seeing the video without super pages, and on the left side, we see with super pages support. In the left side, it's impossible to play the game, but in the right, we are getting near to the point that it could be playable. At least the frame rate is almost the double from one to the other, just enabling the support in the kernel. The other example I have is the Resident Evil 4, that we can see that on the left, with super pages support, it's more fluid, the transition. And if you are we're checking the frame rate, it's like a 60–70% of improvement. So this is something that has recently landed in upstream in the Linux kernel. And we are now studying how we can take advantage of that for other things, like increasing the size of the command list to use a big page instead of 4K pages, and this would remove the number of access that we need to do to the page table. We have other smaller improvements that they are also interesting, that we moved the performance counter definition that we have in the kernel and in the user space completely to the kernel space. So now the driver checks the hardware that you have installed, which performance counter has enabled, and deals everything in the kernel. And the other interesting thing is that last year we enabled GPU stats so you can use the generic GPU top application to know how are the usage of the different hardware queues. And now we enable the memory usage, so we can see there in the first column the number of megabytes that is using each of the different applications, because sometimes the people didn't know which was the application running out of CPU memory. And well, now I'm moving to the user space part, where we have been doing some performance improvements focused on this GPU limited scenarios using big target resolution like full HD. In the case of the Raspberry Pi, full HD is big. And we have analyzed the performance on B3D using several GLS bench traces, and we achieve performance improvement of around 40% in these scenarios. This showcases the difference in performance in the average frame per second from last year, when that is the Mesa version that is installed in the bookwork release of Raspberry Pi OS, and current Mesa that is from 2 days ago. I was getting that collection during the flight to Montreal. And well, you can see that some cases we get an 80%, and in other cases we get a 10%. But the average is significant, it's at 40%. So then when we did that measure, we tried to understand what change has caused this performance improvement. Because we say, well, that was huge, and we didn't identify something that showcases. This is not general for all traces. For the GFX bench, it happens. For other, we didn't figure out that. And we made a study about different branch points. What was the change of for a year? What was the change of the improvement? So we identified that there was an improvement in before 24.1. We see that this is the percentage of improvement, and it's clear there. We have other improvements over the time, but this is the bigger one. I was pointing to a patch when we were implementing this texture barrier extension for OpenGLS, that at the end is implemented usually by just flashing the jobs that have been already the driver working on them. And we identified when we were doing this implementation that our driver was passing all the tests without doing nothing. So that wouldn't make many sense, because probably we were doing more synchronization that was really needed. The driver was being too conservative. So in cases where a job was reading a resource that had been previously written, it was going to flash the job that was doing the reading. But it is not generally something we need to do if we can use the same job as before. So what we did is we don't flash in the case we are doing this. We are submitting to the same job as before. So what happens if we do this? Instead of having two jobs because of that, we are merging all the draw calls in the same job. And we are avoiding loading all the tile buffer and storing the tile buffer for each job. So this makes a significant improvement. So in order to show this in the conference, I just go to main. I reverted the commit that introduces this new behavior, and I get the number of jobs that were submitted by the different traces. On the left, we have the frames per second of the traces, and on the right, we have the number of job submissions, and we can see the number of job submissions by number of frames. No? So we can see, for example, the reduction on the Aztec demo, that is from 80 to 50, is 40%, or is 40% reduction of the number, total number of job submission, and at the end, we see the cost of this improvement. So just removing that coming from comparing with and without and with the commit, we see that we can now know why we are improving the performance in these traces. Closing with the optimization, we worked also on compiler backend optimization. We managed to, in a year, to reduce the number of instructions with a shared DB set by 4%. We did multiple optimizations. Some of them were related to reducing spillings, others to reduce, in particular, sets of CTS because the traces were the CDDB were not using them. And in general, we see that there is probably around the 20% of the performance improvement we have done in the year was related to shader optimizations at the end. And well, so as I would like to have some space for questions, the next step that we are going to continue to work is mainly on performance, improving both the OpenGL and Vulkan driver. We continue working on the compiler backend that we probably have many things to implement, allowing the scheduling to parallelize more instructions. Work on reducing more load and store operations from the tile buffer, but because we have already identified that we can increase the work on merging draw calls in the same job. Continue working on the kernel space driver performance. And we are already integrating Perfecto for having CPU performance monitoring, and continue working on implementing new OpenGL and Vulkan extensions that are requested mainly by the users of the platform. And that's all. So any questions or comments will be welcome.
Yeah, I just have a comment. You mentioned that you were lacking support for non-seamless cube maps.
Yes.
There is a lowering pass for this in NER, but you might not want to use it. I don't know.
We're thinking on using it. That's the idea. We already know that it's there, but we didn't have still the time to do that lowering to support it. But well, thanks for the comment.
Thank you for the talk, and thank you for all the work. I'm kind of using a lot of that.
Oh.
And one specific question is, how do I use the latest stuff, and does it apply to Raspberry Pi 4?
The latest stuff, nowadays, the best way for using the latest stuff is just to build Mesa from the upstream and install it on the system. That's the easiest way to use the last.
Upstream mean like the upstream, or like do you have a separate branch?
No, we have the regular Mesa branch that you have upstream. No, you don't need nothing particular. Downstream, there are a couple of commits that are just to do some small optimization for the desktop use case of Raspberry Pi OS that are related to try to force, in some situations, to use tiled format or that. There are a couple of commits that we think about some moment to integrate upstream. But as they modify other drivers in Node, with some assumptions, maybe it's not suitable for that.
Got it. So for me, as a going to upstream for kernel, like just manually compiling 6.8.
Yes, we are thinking about in this. We are going to release probably soon a new updated version in Raspberry Pi OS, at least with the commits that we identify that provide some performance improvement.
Thank you. And for pages, do I need to do something, or it's like magically happens?
For super pages?
Yeah.
It will happen when we update the kernel at downstream. In other cases, we just would need to compile a kernel and install it.
So like even like with the right kernel, it will just work.
It will just work because Mesa has some patches to enable that. Check if it's available. If it's available, we are going to do some small changes in that.
Got it. I'm very excited. Thank you.
Okay, thank you.
So as for the super pages, like big and super big pages, will they always be used, or are they based on kind of heuristic of the resources?
Well, they are going to be used based on some heuristics on the size of the buffer that you want to do. But in the user space, we are going to modify, for example, for the command list execution buffer, I think about we are going to get a big page if we have support. In other case, we're going to get the normal ones. So there are some optimization that would improve, that would be available. But the general usage is based on the size of the buffers. Okay, thank you. So if no more questions, we can finish on time, I think. Thank you.
are Eric and Martin, and we have a couple of jobs in GitLab that we need to run. Up here and there. And as you can see, they are stuck. They are waiting on a dot that just doesn't exist, or a test machine that doesn't exist yet. They are here, and let's get started because, well, we need to run these jobs. We have 10 minutes to tell you how good Citron is. Here we go. So what is Citron? It's a bare metal infrastructure that has been designed for people who are under some stress, as in, like, you know, you need to maintain a farm, so you're under stress. We want to avoid a situation where, like CrowdStrike, where the machine just doesn't boot anymore reliably. Oopsie. So we are image-based and fully net booted over HTTPS. So even the boot configuration is stored outside of the machine. It's auto-configured where possible for pretty much everything, everything that we could, and that also includes backup and that configuration. Then for the actual test machines, we aim to be easy to use and very low maintenance. So for this reason, we are also container-based. So everything is loaded, cached, and run by boot to container and interoperability that we developed. That is Podman-based. We have sane defaults. That means that by default, the machine is just going to boot and run what you want. But of course, if you want to have more control, then you can partially override these defaults or fully. And also, we don't have any hard-coded boot flow, and we're going to talk about that a bit later. Okay, so here is the boot sequence of the gateway. So it's going to be a bit easier to see. So first thing, iPXE is a bootloader, is loaded from a USB stick. It downloads the boot script and artifacts from a remote server, authenticated by a client certificate inside iPXE. Then the kernel boots and run boots to container. Boot to container downloads and run the gateway container. Then we have the systemd logs that you saw for a split second, and then the dashboard appears. And this is your Citron dashboard.
Okay, so enough about the gateway. What about the DUTs? Or the test device?
Go ahead.
So for the test machines, we have some requirements on the hardware side. We support x86 64-bit, ARM 32 and 64-bit, and RISC-V 64-bit. We need to have fully controllable power switching, even the battery. So on Steam Decks, for instance, we need to do some modifications for that. You need to have Ethernet network. On some devices that don't have that, we use a USB gadget. And we need a serial console for the real-time logs. On the software side, we support on Android, the Android bootloader, EFI, iPXE, and Raspberry Pi or U-boot. And for the kernel, out of the box, the device is going to be supported out of the box if it has upstream Linux support, and otherwise a recent-ish Linux is enough. So let's assemble the DUTs. So Martin's going to set up everything, each machine one at a time, and I'll explain the boot flow. So first off, we have the Steam Deck. So we use a smart plug to control the power remotely, and it's connected on the battery relay. We plug the network and serial console to I'll have that. And in a bit, we'll press Discover on the dashboard, and it will turn on the PDU port that he just showed, and Citron will wait for a new device to appear. This will happen with iPXE that is going to announce itself with a DHCP request with the user class option, which provides the client architecture as x86, 64, UEFI, TFTP as the parameters. From that, we're going to answer. So yeah, the configuration here is for DHCP requests with called iPXE, which matches a iPXE request of one of those architectures. So for this, we're going to answer with this boot script from a URL. That's this tiny script that we have here with just a kernel and interoperability, which are configured here. Those are the default options, but the job can override those. And it's just going to boot that. And yeah, once it's done with the discovery from that DHCP request, it's going to go in training to make sure that it boots properly. Next, we have the Raspberry Pi 5, again on a smart plug, but this time we were booting an ARM64 machine. But unlike iPXE, the Raspberry Pi firmware does not always identify itself. Instead, we have to rely on detecting the MAC address here, and we have this list of MAC address that we sort from the OUI allocation. And yeah, so then next we just download the Yes, we download the board setup, the DTB, device tree, the kernel via TFTP. We have too many files to expose, so what we do instead is that we download the whole firmware from the Raspberry Pi repository, and we extract the files to, here. We extract these files and we expose them in the correct path so that it can actually boot with these files. And the job can override that or just use that and add something on top. Next, the Vision 5. Martin went faster than me. This one is a bit of a simpler setup, but we're using a power over Ethernet switch to provide both power and network together. And this one is a RISC-V board. Last one is an Android, and this one we use fastboot to boot it, which is different. It's not a network request, it's a new USB device that pops up.
Yeah, and now here is the dashboard. Oh, maybe I could make it a bit bigger by closing that. Here we go. Yeah, so what you can see there is that now we have, oh yeah, sorry. That's probably better. So we have detected all the hardware. So we have the Van Gogh here, which is the Raspberry, the Steam Deck. And we can get information about the Steam Deck up here. So we see that it is a 4-core CPU, 16 gigs of RAM, booted using EFI. We can see the bar size, PCI ID, of course, and then the AMD GPU information about it. And that's it. So we have that for every single dot. And it was learned by booting a container that was just checking what is the actual machine that was being used. Then, what do we have next? So we want to expose these machines on GitLab. So what we need to do is say which instance we want to expose it on. Then what type of runner we want. Is it an instance runner, a group runner, or a project runner? We'll need to create a registration token that has this create runner role. And if you want it as an instance type, then you need to have the admin mode also. And then you need an access token with the read API role that allows you to check that the tags that are in GitLab are the same as the ones that we have found. And then you just have a way to expose the runner if you want or not. Very good. Then we can run interactive jobs on it. We don't really have much time for it. But the way you do it is first you connect to the farm using WireGuard. And that means that if you have multiple farms, then you can connect to all of them. Then you just run this command, execute a CTL run. Then you set the tag that you want to use, one or many. you set a folder that you want to, like all the files that are in there are going to be uploaded to the DOT or test machine. And then all the files that are going to be added there by the test job are going to be downloaded back after the execution. So at this point, like you would have all the files from the job. Yes, so actually now we probably should have checked first the jobs. So GitLab, yes, it's started, and it is right now pulling the containers. I don't know how long it's been running for. 3 minutes, okay, and then it started testing VKD3D on the Steam Deck in real time. And then we have the Raspberry Pi. Hopefully also has picked up the job. Yes. No way. Everything has been working. There's no way. Look, it's done. It's been running VKCTS. I mean, the fraction is 1,000, so, you know, pretty fast, but here it is. Up. 999. This is not what I wanted. Okay. So yeah, now you know that you can also run interactive jobs. And now comes the question, like, why did we decide to spend so much time on CItron? Well, that's because we want to make it possible for developers to share the test machines and do it without feeling like they could destroy their setup and rootfs or like change a variable somewhere and then you don't know like what is your boot configuration. So it's terrible. So we want to get rid of that. We also want to obsolete installing and maintaining OSs on your test machine because we just every single boot we send an init from FS that is the OS to run your container. And it's fine. It's just 20 megs, so it really doesn't take much space. And yeah, and of course, being able to run a CI system like this in a hotel room or in a venue here, it's fine. See, no problem. Wasn't stressful at all. So what's next? A ton of things that's not even full. That's all we could think of. But I mean, the gist of it is that we have a lot of features that we want to add that are going to be impacting the design, especially job prioritization and preemption. You know, if you have a long-running job running traces, then you want to be able to run your, well, pretty much jobs from Mesa instantly and then continue the low-priority tasks. So these sort of things are going to be changing a bit the interface, and hopefully we can settle this soon, and then we can have, you know, more people using it. So that's the gist of it. And yeah, that's it. Here are our contact information, and we are, I guess, done because it's not a talk, it's a demo. So I don't know if there are questions. Thanks for listening to the rambling.
matters and is important is there are a lot of quite obvious good
name is Robert Marder. I'm a graphics and multimedia engineer at Collabora, and I'm here to give a short presentation about video offloading on the Wayland Linux desktop, its current state and challenges. And what I'll be talking about is what is it and why do I think it matters? Give a short refresher about the involved hardware and software components to give you a rough understanding what we're talking about. Then shortly go into recent and current development. And finally speak about some challenges and give an outlook on what to expect soon. So what is it? We're talking basically just about efficient video playback on desktops. And this has been possible for a long time on embedded devices. But more recently, we've been finally be able to get that to the desktop as well. And the reason why I think this matters and is important is there are a lot of quite obvious good reasons, I think, like better performance, better battery, longer battery time, etc., etc. However, the part that I find most interesting is the community aspect, because by having these technologies being used by the Linux community on their setups, daily driving them, has a lot of advantages regarding testing. Like if you have a big community using a feature, you get lots of testing on different setups. And at the same time, there's a high incentive for people to, when things don't work, to look into the code, work on it, improve it, make it work on their setups. And therefore, we are directly training new engineers who might then be not only be very competent in this area, but also be highly motivated because they are working on something they're using themselves. And that's something very useful on the strategic side, I think. It certainly worked for myself. So buffer sharing. In short, on Linux, we use DMA buffers or DMA buff. That's a framework to share buffers between hardware and also different subsystems on Linux. And if we focus on hardware decoders, GPU, and display engine, which are the important parts here for zero copy video playback, then to give you a rough idea, like in a simple world, setups would look either like this. You have a dedicated GPU or device which has the renderer, the decoder, and the display engine all sitting on one device and using the same VRAM. And for efficient playback, you mainly need to make sure that things don't go to the CPU or the system RAM and back. And otherwise, you just need to ensure to not have too many copies in RAM or something. And on SoCs, you might, in an optimal world again, have an even simpler case where really everything, all involved components, can access the same memory. You can use DMA buffs just freely to pass them around between the different components, and they never actually have to get copied. However, in the real world, you can imagine it's a little bit more complicated. The most intuitive part probably is multi-GPUs, where you can imagine if you use a decoder on one device and then want to render on it on a different device, or put it on a display connected to a different device, you usually have a way to directly copy between the devices, but you need to ensure that actually they both understand the format in use and the memory tiling, etc., etc. And there's all kinds of limitations on that. But also in the simple cases of just having one dedicated GPU, it's already the case. It's often already the case that, for example, the display engine does not actually have access to all memory or all kinds of features that you use on the, like different memory tiling, etc. So let's say your display engine only has access to a certain amount of video memory. Then you need to ensure you should better not always allocate your buffers in that part of the memory because it will quickly be full. But instead, you need to carefully decide when to allocate buffers in that memory and when not. Similar restrictions apply in many real-world SoCs. A typical example here is that the display engine, again, is a different component, actually, and doesn't, first of all, only has access to a certain amount of memory and also maybe doesn't have an I/O MMU, cannot use virtual memory. And this you need to allocate in a very specific way to make things work. And on the software side, what you usually have is you use some kind of multimedia framework like GStreamer, for example, which then has decoder elements which talk to the kernel, which then talks to the actual hardware decoder. Then this multimedia framework needs to interact with the toolkit that you will most likely be using, for example, GTK4, and then both sides need to negotiate about which formats, etc. Again, they support and need to pass through all this information. And the toolkit, again, will then usually talk to the Wayland compositor. This is the Wayland part in all of this. And allow pass buffers through. And that compositor in the end will then again finally talk back to the kernel and to and to the display engine. So the takeaway from this is we need a lot of info to make good decisions about buffers, where to allocate them, by whom, and pass all relevant info through, so all these components can work well together in a generic environment. A major step forward here has been explicit modifiers, which by now have been plumbed through to a lot of components, and this made things much, much easier and better. However, we're still not done yet. We will probably need even more APIs, notably about DMA heaps. I will come back to that later. So what have been recent and current developments? I'm sorry, I only have very limited time, so I can only go into a few examples here. However, what I found quite noteworthy is especially the GStreamer 1.24 release, which finally introduced modifier, a new API, which is DMA specific and has support for explicit modifiers. again, this has made things much better on a lot of on many sides. Noteworthy is this is an ongoing effort, and quite a few elements don't support that yet, however, are being in the process of being converted. Noteworthy here is that the VA API and default to stateless elements already support that explicit modifiers. However, default to stateful does not yet, and that will be required to enable zero copy. This is actively being worked on, by the way, and we have for a long time having had working proof of concept, which will hopefully find its way into upstream soon. On the compositor side, there's been a lot of movement over the last year. MADA finally landed support for video formats like NV12, which is commonly used for which is commonly the format used by video decoders in version 45 about a year ago, and Kwin 6.0 that was released earlier this year did the same, which is great because that means now on both major desktops we have support for video formats in Wayland. On the toolkit side, GTK 4.14 was a big release with coming with support to offload buffers to Wayland subsurfaces, which then can be used by the compositor to offload to the display engine, for example. That was also earlier this year. And more recently, now with the GNOME 47 release, the GTK4 Paintable sync, which is the recommended way to interface between GStreamer and GTK4, got a lot, also got support for all of this. So now the whole pipeline from GStreamer up to the compositor is in place, and will be shipping apps that support this by default. More on this later. Another part worth noting on the browser side is Chromium, which has support for a lot of this already, which was mainly developed for the Chrome OS effort, which, as you may know, recently got halted. However, there's ongoing work to bring this finally, to make this work on the generic Wayland backend. And I hope we will see that soon. So what are the main challenges? When we're dealing with the three common graphics APIs, DesktopGL unfortunately doesn't have native support for video formats at all. It is possible to use custom shaders in some situations, though, to still, in many situations, though. GLES does have native support. However, there are limitations regarding the color formats, the exact color representation, which is not guaranteed by the API. And all of this will get much better with Vulkan once it really the more toolkits and apps get ported to Vulkan, the easier all of this will get. The other big development is, of course, color management and HDR in Wayland. There has been a lot of progress lately on this. Both GNOME and Kwin ship with preview versions of the protocol, which unfortunately hasn't landed yet. However, there's good chances that by the time the next big releases come in spring, we'll finally have support for that. Demos. I wanted to show some videos to give you some better idea about all of this. However, I don't have enough time for that. So instead, you can just install Showtime, for example, from FlatHub, or from, if you're on a recent distribution, just from your package manager, and try it out and see how well that works for you. So thank you. Thanks for your time. I hope there's some time left for some questions. And by the way, we are hiring. Thank you.
Now we can go back to the phone, right? Next question. Seems like nobody has questions.
All right, hey Robert, thanks for all the good work in the video offloading side of things. I see you mentioned Chromium, and it is surprising.
Seems like nobody has questions.
Hello? Okay, I'm assuming I'm audible. But yeah, all right, hey Robert, thanks for all the good work in the video offloading side of things. I see you mentioned Chromium, and it is surprising.
Seems like nobody has questions.
Hello? Okay, I'm assuming I'm audible. But yeah, all right, hey Robert, thanks for all the good work in the video offloading side of things. I see you mentioned Chromium, and it is surprising. Hello? Okay, I'm assuming I'm audible. But yeah, all right, hey Robert, thanks for all the good work in the video offloading side of things. Chromium, and it is surprising.
Maybe you can write your question down and hold it up.
That's a good idea.
Can you hear me from this microphone? Okay. All right, I'll use this. Yeah, so on the Chromium, I also noticed that on Chrome OS, Chromium's actually doing, video offloading to hardware planes and all that stuff. And it surprises me that it's not available on the Wayland side of things. So from your perspective, what is the remaining work to be done there? Like, what's preventing this from the plane offloading from happening in Chromium? Hardware planes and all that stuff.
I'm sorry, I'm getting an echo now,
Available on the Wayland side of things.
and I can't understand you anymore.
From your perspective. Okay, can you hear the question like this? Yes.
Yeah.
Okay. Just speak loudly, not too much in the microphone, so we can hear you through the laptop. Sure.
Maybe I'll just walk on this side so it doesn't ping.
Yeah, just walk over here. Okay. Come here and just keep this in your hand, or we want to hear you in the stream.
Okay, sure. Yeah. So quickly, just ask my question again. Yeah. So I was wondering what's preventing hardware plane offloading from happening on Wayland today for Chromium. because I know that's available on Chrome OS side, but just curious what needs to be done to make it happen on Wayland. Uh-oh. I don't think it's. I can send an email to him after.
Okay, I think I got the question now several times, and I think I got now all parts of it too. I don't have an echo on your side, right? But in very short, I think I got the question now. And now I have an echo on my side. Anyhow, I will just keep talking. The decoding side, which is getting much closer to getting ready to be supported. In very short. Oh, now I have an echo on my side. Anyhow, I will just. The decoding side, which is getting much closer to getting ready to be supported. Okay, it's a bit difficult. Anyhow, decoding needs to just be enabled by default more or less, and then there's mainly just some paper cuts in various places. And certainly, compositors like Western, for example, has way better plane offloading support already than, for example, Mother. And I'll leave it at that for now. But I think over the next couple of months, I hope we'll get closer there. Way better.
by calling those functions that you've seen before, and then matching the best fitting one. So it's pretty bad. It doesn't really support the XKB layout switching. So if you have, like for example, Hans Christian had a problem where his first keyboard layout was Norwegian, his second one was English. He switched to the English, and the wine was still thinking that he's using Norwegian all the time. So that's something we want to deal with. Luckily, there's something called Wayland that's coming. It has more sensible and less verbose implementation of keyboard handling that uses actually all the XKB goodies, and hopefully that can be with some elbow grease adjusted to Wine X11, and hopefully we will be able to borrow most of that. Other than that, the keyboard handling is pretty straightforward. We have to do the usual translation things like sending events when they're supposed to be sent, and X11 doesn't send them, and the other way around, but that's normal. Then we have mice and touch screens, which are fairly straightforward through X input, and fairly is doing heavy lifting here. So now the meat and potatoes. Non-keyboard and non-mice, so mostly game controllers. This is much more complex than the two I mentioned previously. Luckily, there's SDL, which we use for everything that's like a gamepad. So we have multiple backends that are able to pull those devices from different sources. And SDL is one of those. And SDL is a great library because it normalizes a lot of the controller stuff for us. Think about the usual Xbox controller, like, A, B, X, Y buttons, bumpers, some triggers, D-pad, and analogs. And basically, we get all of them in the same form, and we pretend all of them are Xbox controllers. Then we have the usual Linux EVDF, which is readable on most of the machines, but it's already like heavily processed by the kernel, and we use that whenever SDL is not good enough, or like for some more complex devices that game controllers, like flight sticks and other devices. And there's the last one, which is Hydro, which you use for some devices, but not all. And we can rarely actually read those nodes, and more on that a little bit later. So we then normalize all of that into HID form. So even if you get EVDF device or SDL device, we still create a fake HID device out of it inside of Wine. And HID is the USB human input device class. It's a very nice standard that has report descriptors. Basically describes you what the device can send to you or what you can send to the device. And you just read out of it and parse that output and then say to it like, hey, yeah, I want some force feedback, so please vibrate that motor for me. And Windows is pretty HID-centric. You can see it everywhere. It leaks details everywhere. And like if you look at direct input, it leaks implementation details from HID. If you look at raw input, you can basically subscribe on your window for raw HID messages that you will just get, which is not the case on Windows, on Linux, because everything gets parsed. So we normalize everything into that, and that's what gets passed internally inside of Proton. This is how we construct those descriptors. It's basically a template. We say like, yeah, add that many buttons, and then we get a fake device out of it. But we would like to use some of those devices directly, if that's a possibility. So as I mentioned before, we had problems with accessing some of those on Linux, but let's see where that goes. Our case study is going to be this bad boy. This is DualSense controller. Shipped with PlayStation 5, and it has all the interesting stuff. So the normal Xbox-like controllers, so for buttons, shoulders, triggers, analog sticks, but it also has a touchpad, that's the thing in the middle. It also has an audio jack, and also haptic motors, which can play sound, which is wild. So first, to even work with those devices, we have to undo what Linux kernel is doing. Because we ship drivers that patch the descriptors that the device is sending, that's putting them in weird modes. So the HID PlayStation module, whenever you connect this device over Bluetooth, it already puts it into advanced mode. So you just cannot treat it as a normal controller device, because instead of sending the well-described report input number 1, which just says like, oh yeah, this button was pressed, it sends something that's completely opaque. It's not described. It just says like, yeah, this is some vendor stuff. Don't worry about it. So we have to. It makes sense for Linux because the device is exposed by EVDEF, and it also has gyros. It has the touchpad. So you want to expose those, and those are exposed as different devices. But we don't really want that when we access this from the game directly. So this is what we have to do, because so we have to trim the reports. The input report a little bit to 10 bytes, and then shuffle a few bits around because it cannot be consistent with the input report number 1. It's mostly consistent, but few fields are shuffled for whatever reason. Then those devices have something called haptics, and it basically exposes an extra device over USB. It has 4 channels. 2 of those channels go to the 3.5mm jack that you've seen in front, and 2 go to the motors. So if you ever plug one of those devices in your normal desktop Linux and start playing some audio, suddenly you start hearing only mids through your controller. Like there's no bass, there's some trebles, just mids, and it buzzes weirdly. So it would be nice to have some wire plumber rules to help with that, to not default to this device at all, because I guess this is not what most users want. It would be also great to trim down that device. So in Wine, we would love to have access to all 4 channels, but like users on desktop, who wants to play music on their haptics motors, right? So it would be good to have that user visible device as only the 2 channels that actually go to the jack. And then there's other part where on Linux you cannot access the full vendor-specific descriptors. There's Microsoft standard call that allows you to define container ID, and then it allows you to pair devices like from different APIs. So you can pair the audio device to the actual input device, but we don't have that. So we do the next best thing and look at the SysFS paths, and if they are coming from the same USB device, we try to pair them. Then there's access. So on Linux, when you try to access any of the Hydro devices, you get that, permission denied. On Windows, it's a little bit more complex, but basically you just open a file and then you read from it, and you can access almost all devices other than the sensitive ones. So Windows has limits on mice, keyboards, pen devices, touchscreen, and touchpads, because this is what usually like used to type out, type information, type your passwords, and you don't want to have keyloggers sniffing on that. So that's quite a sensible policy. And basically all of the game controllers fall into the second category, where you can just access it in shared mode. So we would love to do that on Linux. And currently in Proton, we are piggybacking off Steam. So Steam ships a set of rules for its Steam input system. So this is the thing inside of Steam that allows you to remap controllers and do a few other things. And they ship a lot of rules to allow user access to those. And as you can see here, those rules for PlayStation 5 DualSense controller over Bluetooth and over USB. And there's a lot of users of Hydro. It's not only Wine Proton. There's also Steam that uses it directly because they ship the rules. There's also SDL, which has Hydro backend. There's also all the software that allows you to configure your mice. Right now, like I think Ratbag runs a daemon as a root and then allows you to access through that, like in some sanitized way. So what we would like to see, and we try to propose that in systemd, was to tag all the game controllers with special tag ID game controller, and then either Upstream can do that, or we can ship a simple UDEF rules file that allows user access on all of those game controls. That would require implementation of like simple hit parser just for the report descriptors. And that probably would work great. Like we wouldn't have to maintain that list ourselves, just a single rule and it works everywhere. What we're getting instead is that heat IO C revoke, IOCTL was merged in kernel 6.12. This allows you to have a descriptor and do that IOCTL on it, and then it basically closes it without closing it and allowing reuse of the FD. You get a message saying that there's no device, no dev. Then also logging D super divide take device, so that's dbus API, was merged. And right now, everything else is kind of in limbo, so that will happen sometime in the future. So we either will need a Wayland protocol support for that, or XDG desktop portal. Looks like it's going to be Wayland protocol. I think that's one of the latest posts by Peter Hatterer said that the Wayland protocol, especially specifically input FD, is going to be the solution here, which doesn't make us happy because that makes the solution Wayland only. And while Wayland is great and we have Wine Wayland in progress, it's going to require much more work and much more protocols before being fully usable and working as well as Wine X11 on X Wayland. So this is a no-go. So maybe desktop portal, that would be better. That would be at least usable. Then there's session manager has to implement that. So all your KDEs or your GNOMEs or your XDG desktop portal W roots would need to implement that. And then we would need to implement support for the portal or for the Wayland protocol inside of Wine. So the request that comes with that is, I think that Leonard Potterlink was fine with tagging things. So I think I'm going to try to revise that. So we would have access to game controllers. And then the last part I think was no-go because of security reasons, but we can probably ship that rules file as like a separate system package getting installed on the desktop. Yeah. That's my little rant on the state of input devices in Linux. Any questions?
So I have some question about DualSense. I guess it's for any controller. You mentioned there was the touchpad and the gyro, but I'm not sure if I'm not quite clear if that is also exposed if HID raw access is enabled or not.
Yes. So Linux currently doesn't do anything when you access the Hydro. The EVDF devices are still accessible, and that's also a little bit annoying because you get a mouse, like a proper mouse from the touchpad, and some games want to parse that themselves, so they have support for that in game, and you get basically two sets of inputs that are competing with each other. So when you try to move that touchpad in a game that supports it and that uses Hydro, then suddenly like the game reacts to it, and then the game sees cursor movement from X, which is not ideal solution. So one other thing that we would love to see is a way of inhibiting those EVDF devices. So if we open the Hydro device, like send IOCTL or just like out of the box, say like, hey, disable the EVDF stuff. And those gyro stuff is part of the more complex descriptor. So the one that's vendor only. But we understand the format, it was reverse engineered. And also like, I think Sony contributed the description of that as a part of the upstream driver.
Okay, I see. So the game uses whatever Windows API, and then one will go to Hydro and then grab the right info.
The game uses Hydro. They understand that data. They just parse it directly.
Oh, okay.
And
so one kind of is just a messenger in here.
Yeah, yes. So we basically open the Hydro device and read data from that, and then just pass it to application without doing basically any processing other than undoing some of the kernel stuff.
Okay, yeah, thank you.
You're welcome. Okay, I guess that's it. Thank you.
My name is Jessica, and I'm an engineer at Qualcomm. And today I'm just going to be going over a proposed design for a simulated DSI panel driver to help validate various DSI host devices. So in this talk, I'm just going to go over a bit of background, some DRM framework background for DSI panels, some background on SimPanel in general, a very quick sidestep on the version history, then the current driver design, and then future work for the SimPanel driver. So first off, just a bit of background on how DRM framework handles the DSI panel probe and attach sequence. So usually most DSI panels are probed on boot up, and what happens is that first, when the DSI host driver is being probed, it'll register itself using the MIPI DSI host register API, and in that API, the MIPI DSI framework will go through the each child node of that device tree node, and it'll register that child as a MIPI DSI device. Then during the DRM panel probe, the DRM panel will first add itself to the DRM panels list, and then it will attach itself to the host as using MIPI DSI attach. And then as part of that, that will trigger the DSI host to be added as a component for the overall DRM display driver. So during the component bind for the DSI host, the DSI host will grab the DRM panel through a series of OF API calls, and then it will attach that DRM panel as a bridge to the DSI host. So as you can see, there's a lot of dependency on the OF API, and thus a dependency on the DRM panel being defined within the DT itself. So basically, right now, the way to validate various DSI host configurations is to actually have the physical panel with the configuration you want to test. So there's a lot of disadvantages to this way of validation. It's not very scalable. It's also pretty logistically inconvenient, since you can't really, it's really hard to have every single panel that represents every possible configuration for a DSI host. And also, on top of that, not all panels are readily available to the public. So it can be hard to test some specific configurations. One example of this is just how command mode and video mode are validated for DSI drivers. The MSM DSI driver is one of the few drivers that's regularly validated using command mode panels. And most other DSI drivers will be validated with video mode panels. This causes a pretty big hole in the test cases being validated, since a lot of major mobile SoCs will actually ship with command mode panels, and also with some pretty complex features, like the ability to dynamically switch between command and video mode. So in that case, why not have a panel driver where you can simulate a DSI panel? So that would allow us to test configurations, DSI configurations, where we don't have the physical panel available to us. And not only that, with SimPanel, you can actually adjust for panel configuration and catch DSI bugs on the fly without actually having the DRM panel driver available. You can also integrate this into CI, and you can use this to batch test panels and even do better regression testing. And on top of that, the Qualcomm downstream has already been using simulated DSI panels to do validation for the past 6 or 7 years. On the right-hand side here, I actually have an example of a simulated panel DT node. Unfortunately, we can't just port this one-to-one into upstream, since the SimPanel doesn't have any hardware resources, so we can't add DT bindings for this. And in fact, that was knocked when we asked the bindings maintainers about this. So another alternate that people might ask is why not use EDID? First off, EDID unfortunately doesn't support a lot of DSI configurations. So with EDID, you can't really specify DSI mode flags, DSC information, or other compression algorithms. You also can't specify the number of DSI lanes, etc. The DRM framework components aren't created without a panel being probed either. So you might not even be able to load an EDID and configure the DRM before a panel is actually probed. So yeah, aside of with the version history, so initially when we added the cPanel driver, we specified it as an MSM specific driver. So basically, you can only enable it with the cPanel enabled MSM command line argument. And also initially we wanted the user to be able to configure the cPanel via module parameters. We got a lot of great feedback from this first version. And just to summarize, the feedback was basically using module parameters was not very scalable and it's not very user-friendly either. So the suggestion was to switch to using the ConfigFS API instead. So now onto the current driver design. So right now the cPanel series is kind of split into two parts. The first one is framework changes. So as I said in the very beginning, the real panels are very dependent on OF APIs. So we had to add a few cPanel specific APIs to sidestep all this OF dependency. So if the cPanel module is enabled, instead of going through each child DT node, the DSI host will register the cPanel as the sole DSI device for that host. And it'll just hardcode the cPanel information instead of grabbing it from the OF node. And for the bridge framework, instead of finding the panel or bridge via an OF node, we'll just find it by the driver name. And the second part is just the cPanel driver itself. The MIPI DSI driver ops are pretty similar to that of a real panel. The major differences are just like how and when the panel is probed, and then also the ConfigFS. So the cPanel can't be probed on boot up. You actually have to probe it explicitly yourself via a ConfigFS node. So in order to set up the cPanel, you first have to create the module by doing mod probe on the panel simulation kernel module and mount the ConfigFS. The user can then create like a test panel ConfigFS group and then configure these two nodes. So the first one is the modes node, and that's just to specify the supported DRM mode. The second is the mode flags node, and that's to specify the DSI mode flags. The user will then enable the cPanel by passing in the DSI host device name to the enable node, and that will trigger the panel probe. So all in all, this is basically how the probe and attach sequence goes. When the DSI host driver is probed, it will just register the cPanel as a DSI device. After the device boots to shell, the user can do the setup I described in the last slide. And then after they trigger the enable, that's when the panel will be probed and the panel will be added and attached to DSI. And then during the DSI bind, instead of doing all those OF API calls, it will just do the cPanel specific framework calls. So yeah, this is just a summary of how to use the cPanel ConfigFS. Like I said, you first have to mod probe the module, then mount the ConfigFS, create the panel group, configure the ConfigFS nodes, and then enable the cPanel. Yeah, so there's definitely a lot of work that still needs to be done for cPanel. First off, adding way more configuration options. We'd like to add the ability to specify multiple supported DRM modes, the ability to configure DSC, specify panel DCS command length, specifically since sometimes devices might operate in different modes depending on if it's a larger or smaller payload. And then finally, the ability to configure it so that a panel can be controlled by multiple DSI controllers. And then if all these configurations get complicated enough, we might even add eBPF support for cPanel. And yeah, if this is interesting, I suggest you follow the current discussion around this series on patchwork, the DRI Devil, the DRI Devil mailing list, or yeah, feel free to come up and talk to me about cPanel. Yep. Any questions?
I was just curious if you said this data isn't in the EDID structures. Do you know if it's present in things like display ID or successors to EDID or EDID extensions or anything like that, or does it just not make sense because you don't have the same auxiliary transport to get it?
So overall, the EDID can be helpful in describing like the supported modes for DSI, and in fact, in the Qualcomm downstream, there is some API there is some way to represent like the supported DRM modes as an EDID. The issue is just that the EDID can't represent all of the DSI configuration aspects. Yeah, so you can't have just the EDID and use that to configure a DSI host. All right. Yeah, thank you so much.
Hi, everyone. My name is Daniel Dadap. I'm an engineer on the NVIDIA Unix graphics team, and I'll be talking about switching dynamic display muxes. We can start with a little bit of background. If my slide will advance. I think I need to move my pointer on the screen. There we go. What is a dynamic display mux? Well, folks, we can pop the terminology stack there one word at a time and break it down, starting with MUX, which is an abbreviation for multiplexer. It's a device that takes multiple inputs. It allows you to select one of those inputs to drive an output. On a display MUX, the inputs are going to be connectors, display connectors on GPUs, and the output is a display device. And usually that's going to be on internal panels. It's going to be internal connectors for internal panels on a hybrid GPU system. Very rarely, we do have muxes for external panels as well. And in either case, you're generally selecting between an integrated or a discrete GPU as your input to drive that display device. And this is the sort of thing that you would typically configure at boot time. Maybe in your firmware setup screen, you'll make a selection for one GPU or the other, and that selection will persist for the lifetime of the boot. Unless you have a dynamic display mux, and those are display muxes that are designed to be switched while the output is actually being driven. You'll see examples of this in systems sold with NVIDIA Advanced Optimus branding. When you do have a dynamic display mux, there's a couple of things that you want to see for the best experience. One of those is panel self-refresh. so that you don't have blanking during the MUX switch transition time. And the other thing that you want to see is you want to make that transition time as short as possible to reduce the effect of visible stuttering while you're switching. Let's take a look at some of the typical ways that MUXes are configured. Here's a system with no MUXes. That's the simplest configuration of all. And on this one, we have the internal panel is permanently driven by the integrated GPU. And we have an external panel that's, whenever it's connected, is always driven by the discrete GPU. If you add a MUX to the internal panel, you can now select between either of those to drive the internal panel. You still have the external panel is fixed to a discrete GPU. And you can add an additional MUX to also switch external panel. And you might be confused by the colors. These colors are chosen to represent your favorite GPU vendors. I've mixed them up on purpose just to kind of illustrate the possible diversity of configurations we have here. It's not exhaustive. Besides permuting the vendors a little bit more, you do have, for example, MUXless systems where both the internal and external panels are always driven by the integrated GPU, and discrete GPU is not connected to anything at all. So if you have such a system, what do you do? Why even have a discrete GPU if you're not connected to anything? Well, that's where offloading comes into play. We're probably all familiar with display offload. This is where you have one GPU acting as the display offload source, creating a full screen frame buffer that then gets exported for another GPU to consume as a display offload sink. And the display offload sink then does the scan out even if it's not doing any rendering of its own. If we want to get a little fancier, we have render offload, where instead of exporting a full screen frame buffer, the render offload source GPU exports individual application buffers. Those application buffers are exported to the render offload sink, which combines them with other content to create the full screen frame buffer, and in a sane setup then scans that out. But of course, nobody's going to stop you from doing both at the same time and taking GPU1 as render offload source, sending application buffer to GPU2 as render offload sink, which then is also the display offload source going back to GPU1 as a display offload sink for scan out. And it's very tempting to say, that's silly, don't do that. But if you recall, we might have a system where we're forced to have different displays driven by different GPUs. And in that case, it's hard to avoid. We do have an optimization in the NVIDIA driver where for the special case of full screen render offloaded applications, we can avoid the round trip. But it is something that, in general, you have to consider as something that might need to happen. So how can MUXes help us with that? Well, the core benefit of having a MUX is that if you can switch what GPU the display is physically connected to, then you can completely avoid the need to do any kind of display offload. And if you avoid display offload, then you don't need to keep both GPUs powered on all the time, even if you're only rendering on one. And you also don't have to do a full screen copy over PCI Express all the time. If you have a laptop with a 4K screen at 120 hertz, those full screen copies can be pretty expensive. And that core benefit is possible if you have a display MUX that's not dynamic. Of course, there is a convenience price. In the best case, you're going to have to end your desktop session and lose some state. In the worst case, you're going to have to reboot your system and lose some more state. So that's where dynamic switches come into play. And there's a few different ways that you could kick off one of those dynamic switches. Probably the most naive way is having it be completely explicit. And here's where you can imagine a control panel that has some kind of user interface element that lets the user, toggle on demand one GPU or the other. But we can also do implicit switching. And if you remember that special case for full screen render offloaded applications, that's kind of the poster child for implicit switching here. because again, you have something that's being rendered on one GPU and then displayed on another. And in the full screen case, that basically collapses to display offload. But if you switch the MUX, then you can take that display offload out and do direct scan out and get all the benefits of direct scan out. You could go fancier and even do switches while you're compositing applications that are being rendered on multiple GPUs. That's definitely possible. If you look at macOS and some of the, MacBooks Pro that have dynamic display MUXes already, it's something that's being done. But in any case, whatever your policy is for doing a dynamic switch, whether it be explicit or implicit or what have you, support is needed both from Wayland compositors and from the GPU drivers on both sides of the switch. If you're a GPU driver, you don't really care so much which of those use cases we're looking at. If you're a Wayland compositor, these are listed in roughly increasing order of complexity. And of course, for the GPU drivers, you're going to need some infrastructure to support all of that. Let's take a look at what happens during a MUX switch. The first thing, of course, is the MUX switch needs to be initiated. So that's going to, again, happen through one of those example policies, for example. And once the MUX switch is underway, the GPU drivers on both sides of the switch are going to need to coordinate. The sorts of things they might need to coordinate on could be, for example, making sure that the brightness level stays the same across the switch. If you have brightness controlled independently by each of the GPUs, you might want to get that from the switch away from GPU and prepare the switch to GPU to make sure, and there could also be some translation of levels there. Another thing that we could be doing during this stage is remember that the GPU that's going to be switched to isn't actually connected to any display at this point. If you want to start preparing for the switch, here's where something like proxying, DP, DisplayPort, aux traffic could be useful to let the disconnected GPU utilize the connected GPU to prepare for the switch. Then panel self-refresh, we talked about that. That's going to make sure that we don't get blanking and instead have a hopefully very brief pause where we display the same image. The MUX switch itself happens, and there's going to generally be a specific minimum amount of time that's dependent on the actual MUX hardware itself before the link is usable by the switch to GPU. Once that time has elapsed, then the GPU that's been switched to can set a mode, and we can start rendering graphics, turn off PSR, and move happily on our way. So I did talk a little bit about we're going to need some infrastructure for GPU drivers in order to support this, besides the work in the GPU drivers themselves. What is that infrastructure going to look like? Well, it turns out we have something in Linux already. It's called VGA Switcheroo. It's been with us since 2.6.34, so quite a while now. And on the surface level, it seems kind of perfect for what we need. It's got a concept of a MUX handler driver, which is going to be what's driving the actual MUX hardware itself, as well as client drivers, and those are going to be the GPU drivers. And they all register with subsystem, and once it has two clients and a MUX handler, it automatically turns on and exposes its functionality. And in a lot of cases, the client drivers, the client driver and a MUX handler are both registered by the DRM KMS driver for one of the GPUs. There are optional callbacks that clients can implement to be run before and after the switch. Those can be used for the sorts of things I was talking about, for coordinating certain events during the switch process. And that looks great. Why don't we use it? Well, here's where we start running into trouble. And this is going to be kind of the source of a lot of our challenges here. In 2010, when VGA Switcheroo was introduced, X did not support multiple concurrent OpenGL implementations. So there's some design fault from that, and resulting functional challenges. And kind of the biggest one here is because you couldn't have more than one GL implementation working in X at the time VJ switcheroo was designed. The design assumes that you can't switch the MUX at all while you're driving the output. And that's sort of the whole thing of dynamic MUX switching is we're switching while we're driving the output. In VJ switcheroo, if one of your client DRM KMS drivers has a mode setting client ref count that's non-zero, you get no switch at all. Unless you force the switch, there is something called a MUX only switch, which you can force a MUX switch even if otherwise the can you switch the MUX test fails. But if you do that kind of MUX switch, it bypasses the driver callbacks, and we kind of need those in order to do our coordination. Another functional challenge with VJ switcheroo is that there's only support for a single MUX and can only have exactly 2 inputs going into it. If you have an existing system with multiple MUXes, they are out there, then all of the MUXes are driven together as a single logical device, even if the hardware might otherwise support individual addressing. And that's also a problem for dynamic MUX switching. Some of these functional challenges are reflected in the user space API. The big one, again, is this single MUX dual output assumption that's baked into the user space API. There's also no natural synchronization point between switching the MUX and doing kind of mode setting work. And another one, this is unrelated to the rest of the design, is that the user space API is in debuggFS. And if your distro has disabled debuggFS for security reasons, then you're out of luck and no VJ switcheroo for you. These challenges are not insurmountable. We could work through and add a new UAPI to VJ switcheroo that does not have those limitations. We could introduce a new type of MUX switch that doesn't check for mode setting clients, but still calls the callbacks. But there's another way forward that I think makes a lot of sense. I'm kind of going to try to make the case for, and that's using DRM KMS instead. And why DRM KMS makes sense here is because, again, when we're contrasting a dynamic MUX switch from a non-dynamic one, the difference is that in a dynamic switch, you're actively driving the output. And what's driving the output is going to be a DRM KMS mode setting client. And that client is actually going to need to coordinate a lot of the stuff around the MUX switch anyway. So we might as well extend the DRM KMS API to support dynamic MUX switches. And this idea is kind of so intuitive that actually NVIDIA and AMD and maybe even others came up with it independently. There's a proposal a little under 2 years ago on the DRI development mailing list to that effect. And more recently, AMD had a proposal a few months ago at the DisplayNext Hackfest in Spain. And there's a couple of minor differences. I'm not going to go into detail about the proposals themselves, but broadly, everyone seems to agree, fundamentally, DRM KMS makes sense as a place to do MUX switching. And kind of the core reason it makes sense, it has to do with the physicality of the MUX itself. And if we go back to what's on the MUX, well, what's on the MUX is display connectors, and we have exactly an object that corresponds to that in the DRM KMS API, which is DRM connector. And if we add connector properties to sort of map the relationship between these connectors and a MUX on the system, and that's going to be just a really natural way for clients to discover the availability of a MUX and to understand the relationship between connectors on different GPUs that are actually potentially driving the same display. So if we do MUX switching in DRM KMS and use the DRM KMS user space API and extend it to do that, then it actually solves the problems we have with the VGA switcher user space API as well. One of the easy ones right away is that we don't depend on debuggFS anymore. We depend on DRM instead, and DRM is a natural, sensible dependency. You can't really do any of this without DRM. And the big one also is because we're talking about things at connector level granularity, you can support any number of MUX connectors on any number of MUXes. And those MUXes could also have any number of connectors on them. It doesn't have to be two. You definitely expand the space of hardware configurations that you can support. And we also eliminate the assumption that the connectors on the MUX are going to be exactly one is a discrete GPU and one is an integrated. You might have other configurations. You might even want to MUX connectors on the same GPU for reasons I'm not creative enough to imagine. And also, the compositor or other mode setting client might already need to do an atomic mode set. So you could make the MUX switch request become part of that atomic mode set request. And also, with VGA switcheroo, we talked about there's no natural synchronization point. With DRM KMS, you naturally synchronize things that are happening in the MUX switch with events that the DRM KMS client is actually driving. So there are definitely some open design questions. One of them is, and this is kind of the main difference between the AMD and NVIDIA proposals that we have here, is whether you want to have a dedicated MUX class and, a ioctl for some MUX file on, in sysfs versus, setting connector properties and building that into your, KMS atomic commit request. Another is you're going to need to do authentication across the devices. If you're doing the dedicated MUX device, then you're going to need to prove that you have DRM master on both of the devices owning the connectors on the two sides of the switch. If you're going to be doing it as part of an atomic commit request, well, an atomic commit request, you only have one DRM device there, so you need to prove master on the other device too. Discovering the topology of the MUX is another kind of open design question. It's really easy for the naive case of we have only an internal MUX, which is going to be most of the cases, because you can just key off of whether you're looking at internal display connectors or not. But if we want to support other configurations, that's something that will probably need to be fleshed out a little bit more. We also need a way to query attributes on the connector that's not connected yet. I mentioned DisplayPort aux proxying as a possibility. Maybe there's other things that we could be doing too. And another open design question is how to switch a MUX that isn't connected to any panels yet at all. So for an external MUX, for example, you may want to switch it, and this would really only make sense for an explicit switch. And I should say too that explicit MUX switches are really the only kind of switch that makes sense for external panels anyway, because with an external panel, you don't have control over things like how long the panel takes to recover from mode set. It could be on the order of seconds or tens of seconds. You don't want that kind of thing happening without the user actively being behind that decision. If we have a design where we're using a dedicated MUX class and there's actually a separate, UAPI for the MUX switching that's not part of doing, atomic commits, then that's probably a main reason to favor that design. Let's take a look just at how this would sort of be built across the stack, and starting from kernel space, obviously DRM KMS is going to be central here. The GPU drivers on both sides of the switch are already DRM KMS drivers, and we would have a MUX handler driver analogous to the handler drivers in VJ Switcheroo registering with DRM core as well. In this example, the MUX handler uses ACPI to drive the actual hardware. That doesn't have to be the case. That's just an example here. Then the GPU drivers are going to export connector objects in user space, and here's where our properties come into play. These connectors are both saying that they are associated with MUX number 0, and then they each have an index on that MUX. And if we're doing a user space API where we're MUX switching as part of an atomic commit request, then that's all you need. If we are also having a dedicated MUX object, then that MUX object is going to expose a file. It's going to be part of the user space API as well. Then, of course, the compositor drives all that. And here again, I've got, just as an example, applications being rendered from multiple GPUs. Again, just to illustrate, this is potentially something that's got a lot of applications running on it, and the compositor is going to drive the policy based on what those applications are doing. And I guess it should be pretty self-evident that the compositor is the natural choice for driving that policy. Again, the compositor knows what all the applications are that are running, and from all the GPUs. And also, importantly, it has extra context that other layers of the stack aren't going to necessarily, that would help sort of break the tie on tricky situations. So my go-to example for this is, again, if we consider that full screen, unredirected, render offloaded application, and then you hit Alt-Tab, and now all of a sudden you're not really full screen anymore because you're partially occluded. And here's a place where the compositor could decide, well, if it can do rendered composition on that GPU, it can decide to do rendered composition for that Alt-Tab pop-up without switching the MUX until that pop-up is dismissed, and then either you're back in full screen, in which case not switching the MUX is the right call, or or you've gone to windowed mode or to some other application, and in which case you'd want to switch. Another example is desktop notification. Same idea. If something pops up, you're not really full screen anymore on that on that application. But in order to do this, we need more robust multi-GPU support from compositors. There's a couple of things that stand out right away, and the first big one is that the compositors are going to need to be able to directly scan out from any GPU on a multi-GPU setup. And this is actually useful even if you don't have a MUX, and if you're not planning on doing MUX switching at all. If you remember the MUX-less system where we have different panels being driven by different GPUs, you're going to want to do this anyway. And there's a link later for a prototype implementation of that. Then the next step would pretty much be to do rendered composition on any GPU. And again, when the Alt-Tab desktop notification stuff, if you can do rendered composition there, then on all the GPUs, then you might not need to switch the MUX for that sort of thing. This is also useful even if you're not MUX switching, because it allows you to avoid that round trip case. If you can do rendered composition, always do rendered composition on the GPU that is actually connected to the display, then you will avoid the need to kind of do that round trip render and display offload dance. And another thing that could be helpful is tracking buffer residency as part of the DMA buffer protocol. That's just kind of nice information for the compositor to help make these decisions if it can easily know, which GPU owns which buffer, and more information to drive that policy. So there's, yeah, for a lot of the open design discussions, I think one thing that I would like to inform those design decisions is sort of what makes sense for the compositors. If you have kind of opinions on that, we can talk about that. Maybe in the hallway track, you can find myself or Austin, my colleague here, would be happy to talk about that. I know this is just a wall of links right now, but these touch on some of the things I talked about. Shout out to Mario at AMD for number 3 and 4, Austin for number 5, and Zaver, who's here as well, for number 6. That's it for the presentation. We have a couple minutes for Q&A if anyone's got any questions. Thank you.
I have a very basic question. So is there any hardware differences between like the normal MUX and dynamic MUX, or is the difference just firmware, software?
So the hardware is fundamentally the same, right? At a fundamental level, the non-dynamic MUX and a dynamic one can do, the same basic function, which is to switch the display. But yes, there's, at least for NVIDIA Advanced Optimus, there's tighter requirements on things like the transition time, and PSR is going to be a requirement for a system, and that'll goes to, making sure that you have a good user experience. I think there are systems out there which don't have things that were designed for dynamic MUX switching that you could probably do a dynamic switch on and maybe just have a suboptimal experience. But there are definitely also ones where the only way to flip it is at boot time. But the hardware itself would be fundamentally the same. Maybe the newer ones that are specifically made for dynamic switching are faster.
I see. Thank you.
Yeah, I don't know if I haven't kept up with the MUX stuff in recent years, but I know back in the day when VGA switcheroo and stuff was added, that you used to be able to at least switch the MUXs on the like I2C and DP aux channels independently. I don't know if that's something we might want to consider here, because rather than like proxying DP aux, you could switch the MUX beforehand for that, query it with the other monitor to get ready so that you knew.
Yeah, so in VGA switcheroo they do have a concept of kind of a split switch. And that's where, for example, I2C might be muxed separately from the actual video signal. And yeah, VGA switcheroo has a bunch of machinery in place for that sort of thing, where you can say, okay, I just want to switch the I2C line for now, and then and then switch the display line later. That is not possible on all muxes. So, but yeah, that's definitely. For the sort of coordination aspect of it, that is another possibility. I think having the GPU drivers be able to coordinate more directly through DRM would help solve things for the more general case where you might have a monolithic MUX that that can't switch those things independently. Right. Yeah.
Thanks.
Mm-hmm.
Hey, can you hear me right?
Yeah.
So I'm just curious, MUXless displays have traditionally been like a very significant pain point for like VFIO users, where if you want to like pass in a GPU to a Windows virtual machine, and then you shut down the virtual machine, and then the virtual machine, even though it's gone, you'll have your NVIDIA device driver still bound to VFIO PCI. I'm kind of curious, like, is this particular mode of transitioning back and forth between different MUXs, do you see there being a potentially more elegant way of accomplishing that, like transitioning the GPU, not just between like which one is going to handle the display for rendering and which one is going to be doing 3D rendering, but maybe like going into virtualized environments and coming out of virtualized environments? Is there some way that we could like intermingle what you're doing with like the VFIO driver?
Yeah, I mean, for VFIO, it sounds more like the challenge has to do with kind of leftover state. And what you're describing sounds more.
Yeah, it's like binding it in SysFS.
Yeah, I'm not sure if it would be as helpful. I mean, maybe just as a workaround, you could make sure that you've switched all the display outputs away from the discrete GPU, just so that there's nothing there for it to. But yeah, I'm not. Yeah, I'd have to think a little bit more about what the interplay would be there.
Yeah. I have one follow-up question, if that's okay. I'm not sure if you've seen the NVIDIA merge driver, but it's the driver that runs the NVIDIA vGPU Manager utility and the NVIDIA vGPU VFIO module next to traditional like KMS output and actually rendering with the PF. So it lets you have VFs and PFs adjacent to one another. So this is like the non-SRIOV mode, right? It's the 2080 Ti and prior. So that's when they had like VFIO MDev and not SRIOV. In that case, you could use the host like for actually compositing the display and running virtual machines at the same time. And that's actually been done on laptops with like MUX-less laptops where the iGPU handles the display, and then the NVIDIA GPU, can accelerate individual processes or individual virtual machines. I'd be kind of curious to see like maybe there's something there that could be done with KMS where we could control like more elegantly as well which of the processes get acceleration and which ones.
Yeah, I mean, I'm not too familiar with virtualization stuff, but it sounds like there may be some overlap between what you're describing and render offload.
Yeah. There's one project in particular I think you should take a look at. It's KMS render only, KMS RO, that lets the device file descriptor. I'll wrap it up quick. I know I'm going long with this one, but it lets the KMS file descriptor and the guest read and write directly to the display controller using a shared buffer. I just want to maybe show you that afterwards.
Yeah, I'll take a look at it. Thanks.
Okay, thanks.
Okay, thanks. I think that's the last presentation of the day. So sorry. Go ahead.
So I'm not sure if this is really related to muxing, but how do you deal? How big of an issue is the need to tile and detile the stuff off the NVIDIA GPU so that you can use it with the Intel or whatever the iGPU is can understand it?
So can you repeat the question? I'm sorry.
How big of an issue is the need to detile off the NVIDIA this stuff so that it can be understood by the other GPU?
Yeah, that's, I mean, I don't know if, James, you know more about how that offload stuff works?
Yeah, I think, we just have to, if we have a tile buffer that we're rendering from our GPU, we have to copy it to a non-tile buffer first before we can display it on another GPU. And usually it also takes care of copying it into a buffer that the other GPU that's driving the display or whatever, our display controller can read as well. So that's usually a step in render offload already. But yeah, that's one of the things we want to skip if we're doing direct scanning.
Okay, so the entire discussion about the DPOX channel made me think like, hey, we also have monitors that do audio, and GPUs have kind of an attached sound device for that. Like, how does that work with MUXes and switching?
Yeah, so VJ Switcheroo does also handle, I kind of skipped over the whole audio issue as well because, yeah, VJ Switcheroo does also have, and that's probably something I should add to the open design questions thing. So VJ Switcheroo also does switching of the audio device as well. I probably need to look a little bit more into how that gets bubbled up to ALSA, and because you're right, you are switching the device that is connected to that audio output as well.
Just probably something for me. I was wondering when reading the atomic commit thing, is it possible to make it atomic? Because if you, like for example, when the first GPU gave out the display, the second one talks to it, and then for some reason couldn't talk to this display, what will happen then? Will it fall back to the first GPU?
Right. That's also something that is a design question I have considered and is open still to. Yeah. So there are a lot of failure paths, and one of the open design questions is what should the defined behavior be, for failure paths? Because what I've kind of envisioned is there's one of the other open design questions is if you'd go the atomic route, are you going to do a 1 commit or 2 commit approach? Are you going to do a switch away commit followed by a switch to commit, or are you going to do a single commit that then DRM core coordinates with both of the drivers to to kind of combine that? I think the single commit is probably easier for compositors, but it also opens more questions about like you have about what's failure going to look like if something depending on what stage that failure happens.
Yeah, because I feel like the receiving GPU, until it actually talks to the panel, especially if it's an external display, it doesn't have any idea to know if it can actually
It is,
work
yes,
with it.
it is a bit of a leap of faith, yeah.
Yeah, and also like especially if like the DRM, oh, not like the HD, like
the HD audio.
Yeah, no, not the audio, like the if you play like a Prime Video or something like that, like the
HDCP.
yeah, HDCP.
Yes. Yeah, the other DRM.
Yeah, the other DRM.
Yeah.
If that's involved, it's probably even more complicated.
Yeah. Oh, yes.
I was wondering if you have well, for HDMI, maxing is complicated, but what about protocols like DisplayPort? Will it be possible to connect a stream, so 2 streams to the same port, and then do the dynamic switching basically in software? Like you'd say to the panel, display this stream, and then display this other stream.
Yeah, I mean, DisplayPort is certainly complicated enough to maybe, I don't know. That's an interesting suggestion. I mean, we are talking about embedded DisplayPort for the common case for notebook internal panels anyway. I assume that, the engineers who design these systems, have decided that having a MUX is easier than trying to have, multiple devices connected on DisplayPort. But I don't know enough about DisplayPort to really untangle that fully.
Thank you.
Yeah. Okay, if there are any more questions, I think this is the last presentation for the day, so I don't know if the host comes back to do anything. Thanks.